Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route towards sleep. Tonight, we're going to spend some quiet time with one of the most famous, most misunderstood, and most dramatic objects in the universe, the black hole. It has a name that sounds simple enough, almost blunt. A hole that is black. A place where light goes in and does not come out again. And yet, somehow, astronomers point telescopes into the deep sky, collect careful measurements, build images, track stars, study glowing gas, and tell us that they can see black holes. That sounds like a contradiction, does it not? If a black hole traps light, why can we still see it? If nothing can escape from inside it, how can it appear in a telescope? If it is truly dark, why does it often sit inside some of the brightest regions in the cosmos, surrounded by radiation so intense that it can outshine entire galaxies? It is a little like being told that a room has no windows, no lamps, no doorway, and no way for anything inside to reach you, and then being shown a photograph of the furniture. Something about that feels suspicious. At the very least, it deserves a slow and careful explanation, preferably one that does not require us to stay too wide awake. Before we drift toward the answer, I would love to know where you're listening from tonight. Are you tucked away in a quiet room while the city settles down outside? Are you somewhere warm, where the night air still holds the heat of the day? Or are you listening in the early morning with a cup of tea nearby and the world not quite ready to begin? And since tonight we're talking about objects where time itself can behave in strange ways, what time is it for you right now? It is a small question, but a fitting one, because every listener arrives here from a slightly different place on Earth, under a slightly different sky, and yet here we are meeting in the same little pocket of attention. If you find this kind of calm science helpful, if it gives your thoughts something gentle to rest on, I would be grateful if you liked the video and subscribed. It helps this quiet corner of physics reach more people who may also want to learn something interesting while letting the day loosen its grip. And as always, do not worry about remembering every detail. The universe has been around for a very long time. It will not mind if you miss a few facts while drifting off. The main idea will still be here, waiting patiently. Just like a black hole sitting in the dark with an enormous amount of gravity and absolutely no concern for your sleep schedule. So let us begin with the puzzle itself. Black holes are famous because their gravity is so strong that beyond a certain boundary even light cannot escape. That boundary is called the event horizon. It is not a solid surface. You would not bump into it like a wall. It is more like a point of no return. An invisible border in space where all possible paths forward lead deeper inward. Once something crosses that border, whether it is a particle, a spacecraft, a beam of light, or a very unfortunate sandwich, it cannot send a message back to the outside universe. It is not that the black hole grabs light with little cosmic hands. It is that space and time are so strongly curved there that every direction that could count as future points inward. This is why black holes seem so absolute in our imagination. They are not simply dark objects like cold planets or unlit moons. A dark planet can still reflect light if a star shines on it. A moon can be seen because sunlight bounces from its surface. Even a piece of charcoal is visible because light from the room scatters off it and reaches your eyes. A black hole, by contrast, does not have a normal surface from which light can bounce back. Light that gets too close does not reflect away. It falls inward. So, if we were trying to see only the region inside the event horizon, we would fail. There is no ordinary light coming from there to form a picture. In that strict sense, the black part of a black hole really is black. But the universe is rarely kind enough to make things that simple. A black hole is not just the invisible region inside the event horizon. It is also the effect it has on everything around it. And that is where the answer begins. We do not see the inside of a black hole. We see what the black hole does to its surroundings. We see gas becoming unbelievably hot as it spirals near the edge. We see stars whipping around an unseen center, We see jets of particles blasted outward from the region around some black holes. We see light bent and distorted by gravity. We see a dark shadow outlined by glowing material. The black hole itself may not shine, but it can force the universe around it to reveal its presence. A useful comparison, though not a perfect one, is wind. You cannot see air itself on a calm day. It is transparent. It does not sit there with a label saying, "Hello, I am air." But you can see leaves bending, grass rippling, dust moving, waves crossing a pond, clouds shifting across the sky. You know the wind is there because of what it does. A black hole is similar in that way, though much less friendly to nearby objects. It announces itself through motion, heat, distortion, and absence. It is seen by its influence, not by its own glow. Imagine a black hole in deep space with nothing around it at all. No nearby gas, no stars, no dust, no companion object, no bright background behind it. Just a black hole alone in a very empty region. That would be extremely hard to detect. It would not glow. It would not reflect starlight. It would not politely wave at our telescopes. Unless it passed in front of something, or affected some nearby object gravitationally, it could remain hidden. This is one reason astronomers think there may be many black holes in the universe that we have not found. They are not rare in principle, but a quiet black hole is not easy to catch. It is the messy ones, the busy ones, the ones surrounded by material, that are much more likely to give themselves away. And black holes can be very messy indeed. When gas falls toward a black hole, it usually does not drop straight in like a stone into a well. Space is not arranged that neatly. Gas has motion already. It may be orbiting. It may be drawn from a nearby star. It may be part of a large cloud in the center of a galaxy. As it falls inward, it tends to form a rotating disk around the black hole. This disk is called an accretion disk, which is a calm technical phrase for a very extreme environment. The gas in such a disk can be heated to temperatures far beyond anything we experience on Earth. It rubs against itself, compresses, collides, speeds up, and releases energy. That energy emerges as light across many wavelengths, including forms of light our eyes cannot see, such as X-rays and radio waves. So when we say we can see a black hole, very often we mean we can see the glowing material just outside it. The black hole is like the unseen drain at the center of a whirlpool. The drain itself may not shine, but the water swirling around it clearly shows where it is. Around a feeding black hole, the surrounding material can become so bright that the region is visible across enormous distances. Some supermassive black holes at the centers of galaxies are surrounded by such bright accretion disks that they become quasars, among the most luminous objects known. In those cases, the black hole is not visible because it gives off light from inside the event horizon. It is visible because matter outside the event horizon is being heated and accelerated in a way that releases astonishing amounts of energy before some of it disappears forever. There is an important distinction here, and it is worth making gently. The black hole does not let light escape from inside the event horizon. That rule still holds. Nothing in our observations breaks it. The light we detect comes from outside that boundary. Some of it comes from gas that is close to falling in but has not crossed the point of no return. Some of it comes from regions farther out in the disk. Some of it may come from jets launched near the black hole by magnetic fields and rapidly moving plasma. The event horizon remains dark. The neighborhood around it can be brilliant. There is already strange enough. But gravity adds another layer. A black hole bends the path of light passing near it. Not only light coming from the disk in front, but also light from gas behind the black hole can be curved around toward us. This means that the image of a black hole environment can look warped, doubled, stretched, or ring-like. We're not seeing a simple object in the way we see a lamp on a desk. We're seeing light that has travelled along curved paths through severely bent space. Some photons may loop partly around the black hole before escaping outward. Others fall in. Others skim past and reach a telescope after being redirected by gravity. The result is not just a glow, it is a glow sculpted by gravity. This is why the first widely known image of a black hole showed something like a bright ring surrounding a dark centre. That dark centre is often called the shadow of the black hole. It is not the event horizon itself in a simple photographic sense, because the image is shaped by light bending and the behaviour of the surrounding gas. But it is closely connected to the black hole presence. The shadow appears because there are paths near the black hole from which light cannot reach us. Against the bright emission around it, that missing light produces a dark region. In other words, we see the black hole partly because it blocks and captures light that would otherwise contribute to the image. Its darkness becomes visible by contrast. That idea may sound familiar from ordinary life. You can see a dark bird crossing the bright moon, not because the bird is glowing, but because it removes light from part of the scene. You can see a person standing in a doorway at sunset as a silhouette, not because their front side is shining, but because the bright background outlines them. You can see the shape of a keyhole because of the light around it. In a much more extreme and gravitationally complicated way, a black hole can be seen as a silhouette against glowing gas. We are not seeing light from within the blackness. We are seeing the edge of absence, surrounded by material that has not yet vanished. Still, black holes are not always detected through images. In fact, for most of the history of black hole astronomy, no one had a direct picture of the shadow at all. Scientists found black holes by noticing that something invisible was exerting enormous gravitational influence. Stars near the centre of our own Milky Way, for example, move around an unseen object with tremendous speed. By tracking those orbits over years, astronomers concluded that there must be a very massive object packed into a very small region. The best explanation is a supermassive black hole. In this case, the black hole is revealed not by a glowing disk but by the motion of stars. It is like watching dancers circle an invisible partner. You cannot see the partner directly, but the movement tells you that something powerful is leading. Smaller black holes can be found in binary systems, where a black hole orbits a normal star. If the black hole pulls gas from its companion, that gas can heat up and emit X-rays before crossing the event horizon. Telescopes sensitive to X-rays can detect these systems even though our eyes cannot see X-rays directly. Again, the principle is the same. The black hole itself is not shining from within. The material outside it is announcing the black hole by becoming hot, fast, and bright. Some black holes reveal themselves when they collide. When two black holes spiral together and merge, they send ripples through space and time called gravitational waves. These are not light. They are distortions in the fabric of space itself, detected by extremely sensitive instruments on Earth. In those cases, we are not seeing black holes with light at all. We are hearing, in a scientific sense, the faint tremor left by their motion. It is a different kind of astronomy, one that does not rely on brightness. A black hole can be completely dark and still leave measurable traces in gravity. So the question, if black holes trap light, why can we still see them, has a layered answer. We see them because not everything nearby has crossed the event horizon. We see them because falling matter glows before it disappears. We see them because gravity bends light around them. We see them because their darkness makes a shadow against surrounding brightness. We see them because they move stars, heat gas, launch jets, and shake space when they merge. We do not see light escaping from the forbidden interior. We see the universe reacting to a place from which escape is no longer possible. That is one of the most satisfying things about this topic. The apparent contradiction is not a mistake. It is the doorway into the real explanation. Black holes are invisible only in the narrower sense. In the wider sense, they are some of the most detectable objects in astrophysics, provided they have something nearby to disturb. They are dark, but not silent. They are hidden, but not harmless to the scenery. They cannot send us light from inside the event horizon, but they can arrange the light outside in ways that make their presence unmistakable. And this is where the story becomes especially interesting, because to understand why that happens, we need to slow down and ask what a black hole actually is. Not just the popular image, not just a cosmic vacuum cleaner, not just a dramatic sphere of darkness in a science fiction sky, but the real physical object described by gravity. A black hole is not a hole in the ordinary sense, and it is not empty in the simple sense either. It is what happens when enough mass is concentrated into a small enough region that space and time change around it in a way nothing else can imitate. Before we can understand the glowing disks, the bent light, the shadows, and the strange ways astronomers detect them, we need to understand the thing at the centre of it all, the object that does not have to shine in order to reshape everything nearby. A black hole begins with a simple idea, but that idea becomes strange the moment you try to picture it. It is not a hole dug into space, like a tunnel through the universe. It is not a cosmic mouth, waiting to swallow everything nearby. It is not a moving patch of emptiness that drifts around like a dark cloud with bad manners. A black hole is a region where gravity has become so strong that the usual escape routes of the universe no longer work. It is what happens when matter is squeezed into a small enough volume that space and time around it are changed in an extreme way. The object may have formed from a star or from a huge concentration of matter in the early history of a galaxy, but once it becomes a black hole, its most important feature is not the stuff it used to be. It is the gravity it now creates. This is worth slowing down for because the name can be misleading. A black hole is not empty just because it is black. The word black tells us something about light. It tells us that light from inside a certain boundary cannot make its way back out to the rest of the universe. But the word hole can make it sound as if there is nothing there. In everyday life, a hole is usually an absence. A hole in the ground is where soil has been removed. A hole in a sock is where fabric has disappeared. A hole in a schedule is a rare and precious thing, usually filled immediately by errands. But a black hole is not absence in that ordinary sense. It is presence taken to an extreme. It is mass, gravity, and curved space concentrated into a region so intense that our familiar ideas begin to lose their balance. The easiest place to begin is with stars. A star is a long struggle between two tendencies. Gravity pulls everything inward, while pressure from heat and nuclear reactions pushes outward. During most of a star's life, those two effects hold each other in balance. The star does not collapse because the heat inside it supports it. It does not explode apart because gravity holds it together. It is a giant glowing compromise, which is also a fair description of many dinner table conversations. In the core of the star, lighter elements are fused into heavier ones, releasing energy. That energy streams outward and helps keep the star inflated against its own gravity. But stars do not have endless fuel. Over time, the core changes. The easy fuel runs low. The star adjusts, burns different materials if it is massive enough, and passes through stages that become hotter, denser, and less stable. For a star like the Sun, the ending is dramatic, but not black hole dramatic. It will shed outer layers and leave behind a dense core called a white dwarf. But for much more massive stars, the story can take a harsher turn. When the core can no longer support itself, gravity wins suddenly. The core collapses. The outer parts of the star may blast outward in a supernova, one of the great explosions in the universe. What remains depends on how much mass is left behind. Sometimes the remnant becomes a neutron star, an object so dense that matter is packed in a way almost impossible to imagine. But if the remaining core is massive enough, even the forces that support a neutron star are not enough. Collapse continues, and a black hole is born. That phrase, collapse continues, sounds simple, but it hides a deep change in the nature of the situation. In ordinary objects, matter has size and surface. A planet has a surface. A star has a visible outer layer. A white dwarf has a boundary made of dense material. A neutron star has something like a surface as well, though it is unlike any surface we know on Earth. But a black hole is different. The visible or physical surface is not what defines it. What defines it is a boundary in space called the event horizon. Once anything crosses this boundary, it can no longer escape. The event horizon is not made of metal or fire or glass. It is not a shell floating in space. If you were falling through it, and the black hole were large enough that the local tidal forces were gentle at that point, you might not notice the exact moment you crossed. There would be no sign saying "Welcome to the point of no return. Please keep your hands and feet inside the gravitational field at all times." The crossing could feel ordinary for a brief while, but from then on every path forward would lead inward. This is one of the most important things to understand about black holes. The event horizon is not a surface that crushes things on contact. It is a boundary of escape. Outside it, escape is possible if you have enough speed and the right path. Inside it, escape is not possible because the structure of space and time no longer allows an outward route. That is why even light cannot get out. Light is the fastest thing in the universe, but speed is not the only issue here. The problem is that inside the event horizon, the future points deeper inward. It is not like trying to climb a hill and failing because you are tired. It is more like discovering that every road, every hallway, every doorway, every possible next step leads farther into the same place. Now, when people imagine a black hole, they often imagine a sphere of darkness. That is not a terrible starting image, but it is incomplete. The event horizon of a simple, non-rotating black hole would be shaped like a sphere. Real black holes probably rotate because the stars and gas that formed them were rotating, and space is rarely polite enough to sit perfectly still. Rotation changes the region around the black hole and creates effects that can drag nearby space along with it. This is called frame dragging, though for a sleepy evening, it may be enough to say that a spinning black hole does not merely sit in space. It twists the environment around it. Nearby matter and light are influenced not only by the black hole's mass, but also by its spin. Black holes can also have electric charge in the mathematics, though astronomers usually expect real ones to have very little lasting charge. Any strong charge would tend to attract opposite charges from surrounding space and neutralize itself. So when scientists describe a black hole in practical terms, they often focus on a few properties: how much mass it has, how fast it spins, and sometimes whether it has any charge, though that last one is usually less important for real astrophysical black holes. This leads to a curious idea. Once matter falls into a black hole, the outside universe does not get to keep a detailed record of what kind of matter it was. A black hole made from collapsed star material, and a black hole that later swallowed gas, dust, planets, or unfortunate leftovers from a cosmic picnic can, look the same from outside if they have the same mass and spin. The black hole keeps the gravitational effect, but not the ordinary details in a way we can inspect. This has led to the phrase that black holes have no hair, which sounds less like physics and more like a complaint from a very picky barber. What it means is that black holes from the outside are described by very few visible properties. You cannot look at a black hole and tell whether it was made from hydrogen, iron, or an old collection of space rocks. The details have become inaccessible. The event horizon hides them. The black hole still has mass. It still pulls gravitationally. It may spin. But the rich texture of the matter that formed it has been reduced, at least from our outside perspective, to a much simpler description. This does not mean black holes are all the same size. Far from it. Some black holes are only a few times the mass of the Sun. These are called stellar mass black holes because they form from the deaths of massive stars. They may be physically small compared with stars, but their gravity near the event horizon is extreme. Then there are intermediate mass black holes, which are harder to find and still an active area of research. They may form through mergers, dense star clusters, or other processes that astronomers continue to study. And then there are supermassive black holes, which live in the centres of many galaxies. These can contain millions or billions of times the mass of the Sun. Our own Milky Way has one at its centre, known as Sagittarius, a star. It is not currently eating material at the wild rate of a bright quasar, which is probably just as well for the general calm of the neighbourhood, but but it is very much there, revealed by the motions of stars around it. It may seem odd that a black hole with more mass can actually have a larger event horizon and gentler conditions at the boundary than a smaller one. This is one of those details that makes black holes both frightening and oddly nuanced. A small black hole can produce very strong differences in gravity over short distances near its horizon. Those differences are called tidal forces. They stretch objects in one direction and squeeze them in another. If a person fell feet first toward a small black hole, the pull on the feet could become much stronger than the pull on the head, causing severe stretching long before reaching the event horizon. This process has a famous informal nickname, spaghettification, which is memorable, unpleasant, and not ideal to think about during dinner. For a supermassive black hole, the event horizon can be so large that tidal forces at the boundary are much weaker. You might cross without being immediately torn apart, though the long-term travel plan would still have serious drawbacks. The size of a black hole is often described by the size of its event horizon, but the mass itself is not spread out across that boundary like a normal surface. According to general relativity, if you continue inward in the simplest description, you reach a place called the singularity, where the density and curvature become extreme beyond the ability of the theory to describe fully. This word can sound like a final answer, but it's more like a warning label on our current understanding. A singularity suggests that the mathematics of general relativity has been pushed to a point where it no longer gives a complete physical picture. Many physicists expect that a deeper theory, one that combines gravity with quantum physics, will be needed to explain what really happens at the centre. So when we talk about singularities, we should be careful. They are not necessarily tiny pebbles of infinite density sitting neatly in the middle. They are signs that our best current theory is telling us very seriously that something beyond it is needed. From the outside, however, we do not need to know the central details to understand the black hole's influence. The event horizon is enough to define the region that cannot communicate back. Gravity outside the black hole depends on the mass and spin. If the Sun were somehow replaced by a black hole of the same mass, Earth would not suddenly be sucked in. It would continue orbiting under the same overall gravitational pull, though the lack of sunlight would make this a deeply unpopular arrangement. This is a useful correction to the common idea that black holes vacuum up everything around them. They do not reach across the universe and pull objects in simply because they are black holes. Far away, their gravity behaves like the gravity of any other object with the same mass. To be captured, something must pass close enough, lose enough energy, or follow the wrong path. Space is large, and black holes are not cosmic cleaning machines wandering around tidying up galaxies. The vacuum cleaner myth probably comes from the drama of black hole imagery. We see artist impressions of glowing disks, stretched stars, and great streams of matter spiraling inward. These things do happen in certain systems, but they require nearby material. A black hole alone does not feed, it waits. If gas or a star comes close, then the situation can become energetic. The gas may form a disk. Friction and magnetic fields can heat it. Some material may fall in, some may be flung outward. Around supermassive black holes, these processes can power active galactic nuclei, where the centre of a galaxy shines with incredible intensity. But the engine of that brightness is outside the event horizon. The black hole provides the gravitational well. The infalling matter provides the light before it crosses the boundary. That brings us to a helpful way to think of a black hole as an object with layers of meaning. At the centre, there is the unknown deep interior, where our theories become incomplete. Around that is the event horizon, the boundary beyond which return is impossible. Outside that are regions where gravity is strong but escape still possible. In those outer regions, matter can orbit, heat up, emit light, and produce signals we can detect. Farther out still, the black hole behaves more like an ordinary massive object, guiding orbits and shaping the environment. The black hole is not only the dark centre, it is the whole gravitational situation created by that concentration of mass. There is another point that helps remove some of the mystery without making the object less interesting. A black hole is not a place where gravity becomes magical. It is a place where gravity follows the rules of general relativity to an extreme conclusion. The same theory that explains the slight bending of starlight near the sun and the tiny corrections needed for satellite navigation also predicts black holes. This is part of what makes them so impressive. They are not separate from ordinary physics. They are ordinary physics pushed into a regime where ordinary intuition breaks down. The universe does not need a special black hole rulebook. It uses gravity, motion, energy, and light, and when enough mass is compressed tightly enough, a horizon appears. How do we know such things exist rather than being only mathematical curiosities? The evidence comes from several directions. We see stars orbiting invisible compact objects with too much mass to be anything else. We detect X-rays from hot gas in binary systems, where a dark companion is pulling matter from a star. We observe gravitational waves from mergers of compact objects whose masses and behavior match black holes. We have images of black hole shadows surrounded by glowing material in the centers of galaxies. None of these observations requires light to escape from inside the event horizon. Instead, they show us the effects of black holes on the world outside. The evidence is like a set of footprints around an invisible animal. You do not see the animal directly, but the ground tells a consistent story. There is also something humbling about black holes because they force us to separate seeing from understanding. We are used to trusting light. Light bounces off things, enters our eyes or telescopes and gives us images. But black holes teach us that an object can be known by absence, by motion, by heat, by distortion, and by gravity. They expand the idea of observation. To observe does not always mean to receive a simple picture. Sometimes it means to collect clues from many kinds of signals and ask what single explanation makes sense of them all. In that way, black holes are not just objects. They are lessons in how science works when nature refuses to present itself plainly. A black hole, then, is not merely a dark sphere in space. It is a compact gravitational object defined by an event horizon. It can form when massive stars collapse, or grow through mergers and feeding over cosmic time. It can be small in size but large in effect, quiet if alone, brilliant if surrounded by gas, and powerful enough to bend light around itself. It does not suck in the universe, but anything crossing its horizon loses the ability to return. It hides its interior completely from outside observers, yet it reveals its presence through the behavior of everything nearby. And once we have this picture in place, the next question becomes sharper. If the event horizon is only a boundary, and if light can move freely outside it but never return from inside it, what exactly changes at that invisible border? Why does light, which can cross empty space for billions of years and carry images from the earliest galaxies, fail so completely near a black hole? To answer that, we need to follow a beam of light closer and closer to the horizon, watching how gravity changes the meaning of escape, until the path outward is no longer a path at all. To understand why light cannot escape the event horizon, it helps to begin with a more familiar kind of escape. Imagine throwing a ball upward from Earth. If you toss it gently, it rises for a moment, slows, and falls back into your hand, or possibly into a nearby flower pot if your aim is as reliable as mine before breakfast. If you throw it harder, it rises higher before returning. If you could throw it with far more speed than any human arm can manage, it might rise so far that Earth's gravity would never pull it back. It would escape into space. This idea is called escape speed. Every object with gravity has one. Earth has an escape speed. The moon has one. The sun has one. The more massive and compact an object is, the harder it is to escape from its gravity. This is often the first explanation people hear about black holes. A black hole is described as an object where the escape speed becomes greater than the speed of light. Since nothing can travel faster than light, not even light can get away. As a first step, that explanation is useful. It gives the right general feeling. It tells us that black holes are not dark because light gets tired, or because the event horizon is a sticky surface. They are dark because gravity has made escape impossible. But if we stop there, we miss the deeper and stranger part. The event horizon is not simply a place where light tries to fly outward and fails because it is not fast enough. Light always moves at the speed of light locally. It does not slow down because the black hole is strong. The real reason is more subtle. Near a black hole, gravity changes the shape of space and time so severely that the outward direction itself loses the meaning it has far away. That may sound slippery at first, so let us approach it slowly. In everyday life, space and time feel separate. Space is where things are. Time is when things happen. You can walk across a room, wait for a kettle to boil, look out the window, and nothing about those basic ideas seems especially mysterious. Gravity in daily experience feels like a force pulling objects downward. Drop a spoon, and it falls. Toss a pillow, and it follows a curved path before landing somewhere inconvenient. We are used to thinking of gravity as a pull through space, but Einstein gave us a different way of understanding it. Gravity is not merely a force acting inside space. Gravity is related to the shape of space and time themselves. Mass and energy curve space and time, and objects move along paths shaped by that curvature. For weak gravity, like the gravity we experience standing on Earth, the older picture works well enough. A ball falls, a planet orbits, a clock ticks in a dependable way. But near a black hole, gravity is not weak. It is intense enough that the geometry of the universe becomes the main character in the story. Light does not need a force pulling on it in the ordinary sense. Light follows the straightest path available to it through curved space and time. Around a star or galaxy, those paths bend gently. Around a black hole, they can bend dramatically. Very close to the event horizon, the available paths become so distorted that light emitted outward may still fail to move farther away in any lasting sense. At the horizon itself, the path that would just barely escape becomes balanced on the edge. Inside the horizon, all future paths lead inward. This is one of the most important ideas in black hole physics, and it is easy to underestimate because the words sound so ordinary. All future paths lead inward. It does not mean that the black hole has built a fence. It does not mean light crashes into a wall. It means that once inside the event horizon, moving toward the center is no longer just one possible direction among many. It is as unavoidable as moving into tomorrow. You can choose where to walk across a room, but you cannot choose to step into yesterday. Inside a black hole, the center becomes like the future in that sense. Not a place you merely approach, but something every possible path carries you toward. A helpful comparison is a river flowing toward a waterfall. Imagine you are in a boat on a wide river. Far upstream, you can row in any direction. If you row hard enough, you can move toward shore or even go upstream. Closer to the waterfall, the current becomes stronger. At some point, if the river flows faster than you can row, even paddling with all your effort will not save you. You may still point the boat upstream, and relative to the water, you may still be moving as strongly as your arms allow, but the river carries you over the falls anyway. The event horizon is something like the place where the inward flow of space becomes too great for light itself to make progress outward. The comparison is not perfect, because black holes involve curved space and time rather than water flowing through a channel, but it gives a useful feeling for why speed alone is not the full story. Light is still light. It still does what light does, but the structure it moves through has changed. From far away, we can imagine a flashlight aimed outward just outside the event horizon. If it is outside, some of its light may still escape, depending on exactly where it is and which direction it travels. But the closer the flashlight gets to the horizon, the narrower the escape routes become. More directions that seem locally sideways or outward lead eventually into the black hole. The black hole takes up more and more of the sky. If you are hovering very close to the horizon, which would require an impossible or nearly impossible amount of acceleration depending on how close you were, the rest of the universe would appear distorted above you, while below you the darkness would cover a huge portion of what you could call the sky. light would need to be aimed within an increasingly tiny range of directions to escape. At the horizon, there is no practical outward route left for a signal starting there to reach distant observers. Inside, not even a perfectly aimed beam has a path back out. It is also worth noticing what the event horizon looks like to different observers. For someone falling inward, the experience of crossing the horizon can be surprisingly uneventful if the black hole is very large. There may be no flash, no hard boundary, no sudden sign. The event horizon is not locally made of something. It is a global boundary, defined by whether light can ultimately escape to the outside universe. That means you might pass it without noticing the exact moment, assuming you survived the surrounding environment. Of course, around many real black holes there may be dangerously hot gas, strong radiation, and violent tidal effects, so this is not a travel recommendation. Physics is good at explaining routes. It is not always good at making them pleasant. For a distant observer watching you fall toward a black hole, the story appears different. Your clock would appear to slow as you approach the horizon. Light from you would become stretched to longer and longer wavelengths, losing energy as it climbed away from the strong gravity. Your image would dim and redden, fading toward invisibility. The distant observer would never see you cross the horizon in the ordinary way. Instead, you would seem to approach it more and more slowly, becoming fainter with time. This does not mean you yourself freeze there from your own point of view. It means that the signals carrying information about your fall become increasingly delayed and weakened before they can reach the outside. The event horizon separates stories. What is finite and ordinary for the falling observer can look endlessly delayed from far away. This delay is sometimes misunderstood. People may imagine that if an outside observer never sees the crossing, then perhaps the object never truly falls in. But in the physics of the falling object, it crosses the horizon in a finite amount of its own time and continues inward. The outside universe simply cannot receive a later signal from inside the horizon. The last light that escapes from near the boundary becomes stretched and dimmed so much that, in practice, it disappears. The horizon is not a place where time stops for the traveller. It is a place beyond which communication with the outside no longer happens. Now, we can return to light itself. Light cannot escape because escaping means reaching faraway observers in the outside universe. Outside the horizon, some light paths can do that. Inside the horizon, none can. This is not a matter of the light being weak. A photon does not carry a tiny rocket engine that can be upgraded. It follows the paths allowed by space and time. Inside the event horizon, those paths do not lead outward. Even if the photon is emitted in a direction that a local observer would call upward, the future of that photon still moves deeper in. The black hole does not need to chase it. The geometry has already arranged the outcome. One reason this is difficult to picture is that we usually imagine space as a fixed stage. In that mental picture, a beam of light should be able to point outward and move outward. But near and inside a black hole, space and time are not a passive stage. They are part of the event. Directions that seem separate in normal experience become tangled with the passage of time. The event horizon marks the boundary where the outward escape route closes. Inside it, moving inward is not like choosing a direction in space. It is tied to the direction of time. The centre of the black hole lies in the future of anything inside. You cannot avoid it any more than you can avoid next Tuesday. Though admittedly next Tuesday usually has fewer gravitational complications. The event horizon also explains why black holes are black, even if there are processes happening inside them. Suppose something emits light after crossing the horizon. That light may move around locally. It may travel from one infalling particle to another. It may still have perfectly normal local behaviour in its immediate neighbourhood. But it cannot become a message to the outside. It cannot climb back across the horizon. The outside universe is cut off from those events. This is why the event horizon is such a powerful concept. It is not merely a dark surface. It is a boundary in causality, a line separating events that can affect distant observers from events that cannot. The word causality means the ordering of cause and effect. In normal life, if you switch on a lamp, light travels outward and someone across the room can see it. Your action can affect them. If you shout, sound travels through air and someone nearby can hear you, unless they are pretending very hard not to. But inside a black hole, any event that happens cannot send a light signal to the distant outside universe. Since light is the fastest messenger available, if light cannot escape, no slower signal can escape either. No sound, no spacecraft, no radio message, no thrown note in a bottle, no very determined pigeon. The inside can influence the black hole's overall mass and spin, because those are already part of the external gravitational field, but specific events inside cannot send detailed news back out. This is why black holes are sometimes described as regions from which nothing can escape. It is a true statement, but it is important to place it carefully. Nothing can escape from inside the event horizon. Outside the horizon, things can still orbit, scatter, radiate, and sometimes escape. Light can pass near a black hole and bend around it without falling in. Gas can circle in a disk for a while, glowing furiously before some of it crosses the boundary. A star can orbit a supermassive black hole for years, decades, or longer without being swallowed, provided its path does not bring it too close. The event horizon is the dividing line, not an infinite suction field. There is a special region outside a black hole where light can orbit temporarily, circling because gravity bends its path so strongly. This region is not the event horizon itself, and the orbit is unstable. A small disturbance can send the light inward to be captured or outward to escape. Around a black hole, this helps create some of the striking visual effects predicted by relativity and seen in simulations and observations. Light from the surrounding disk can curve around the black hole. Some rays may take winding paths before reaching us. Others vanish. The boundary between paths that escape and paths that do not gives the black hole its shadow. But the fact that some light can orbit or bend nearby should not be confused with light escaping from inside. The dramatic light show belongs to the outside region. This distinction matters because it resolves the central puzzle. A black hole traps light that crosses the event horizon. It does not trap all light everywhere around it. The universe outside the horizon remains visible, active, and able to send signals. In fact, the intense gravity can make some outside light easier to notice by heating matter and bending rays into our line of sight. The black hole is dark at its core, but surrounded in many cases by a bright and distorted neighbourhood. It is a little like a perfectly silent person at the centre of a very noisy room. You do not hear the person speak, but you can tell they are there because everyone else is reacting to them. There is another quiet complication. Black holes are not defined by how dark they look to human eyes. Human eyes see only a small slice of light. Much of black hole astronomy uses radio waves, X-rays, infrared light, and other forms of electromagnetic radiation. These are all light in the broad scientific sense, but not all are visible to us directly. When astronomers make images or maps of black hole environments, they often translate invisible wavelengths into colours we can see. So when we talk about seeing black holes, we may mean detecting radiation from nearby gas with instruments, processing signals from telescope arrays, or measuring motions over time. Seeing, in astronomy, often means receiving information, not simply looking through an eyepiece and spotting a black dot with a neat label. The event horizon remains central because it marks the limit of that information. From outside, we can study what happens before matter crosses. We can infer the presence of the horizon from the way material disappears, from the shape of the shadow, from the lack of a solid surface impact, and from the behaviour of orbits and radiation. But we cannot receive ordinary light from events after crossing. The horizon protects the interior from direct observation. It is not protection in a gentle sense. It is more like the universe closing a door without a handle on our side. This leads to one of the deepest questions in modern physics. If information about detailed events inside cannot escape, what ultimately happens to it? This is connected to the black hole information problem. a subject where general relativity, quantum theory, and thermodynamics meet in a very difficult conversation. For tonight, we do not need to solve it, which is good because physicists have been working on it for decades and would probably be annoyed if we settled it too casually before bedtime. It is enough to note that the event horizon does not merely trap light, it challenges our understanding of information, reality, and the relationship between gravity and quantum physics. But for the central question, the answer can be made plain. Light cannot escape the event horizon because the event horizon is the boundary beyond which escape paths no longer exist. Light inside still travels locally as light, but all possible futures for that light remain inside the black hole and move inward. Gravity has curved space and time so strongly that going outward to the distant universe is no longer one of the options. The darkness of the event horizon is therefore not a material darkness, like paint or soot. It is a causal darkness. It is darkness produced by the absence of return. And once that is clear, the next part of the puzzle becomes much easier to approach. If the black hole itself does not send out light from within the horizon, then every image, every glow, every bright ring, every flare, and every telescope signal must come from somewhere else. The darkness stays dark. The light must belong to the region around it, to gas that has not yet crossed, to stars still orbiting, to radiation bent around the edge, to the crowded and heated environment where matter is close enough to feel the black hole's grip but not yet lost beyond communication. That is where the visible story begins, just outside the place where the universe stops letting messages return. So when we say that we can see a black hole, we have to be careful about what the word see is doing. In ordinary life, seeing usually means that light leaves an object, or bounces off an object, travels through space, enters our eyes, and gives us an image. You see a cup because light reflects from its surface. You see the moon because sunlight reflects from its dusty ground. You see your hand in front of your face because light from the room scatters from your skin and reaches your eyes, unless the room is completely dark and you're trying to find your slippers, in which case physics becomes less helpful than patience. A black hole does not work that way. The region inside the event horizon sends no light back to us. It does not shine like a star. It does not reflect light like a planet. It does not have a visible surface that can be photographed in the normal sense. If all we had was the event horizon itself floating alone in empty space, with no matter nearby and no background light behind it, it would be almost impossible to notice from far away. But most of the black holes we study are not found by staring at a lonely patch of darkness and waiting for it to introduce itself. They are found because the space around them is active, matter moves around them, gas heats up near them, stars orbit them, light from behind them gets bent by their gravity. Sometimes they sit in the centres of galaxies, where there is enough dust, gas and starlight to make their influence stand out. Sometimes they have a companion star and steal material from it. Sometimes they collide with other black holes and shake space itself. So the answer to what we are actually seeing is not light from inside the black hole. We are seeing the response of the outside universe to the black hole. We are seeing the bright, distorted, moving, heated and sometimes missing light around the place where light can no longer return. A good way to think about it is to imagine a drain in a bathtub, though we should be gentle with the comparison because a black hole is not literally a drain, and space is not literally water. Still, the image helps. If the drain itself is dark and small, you may not see it clearly under swirling water, but you can see the whirlpool. You can see leaves or bubbles spiral inward. You can see the motion of the water change as it approaches the centre. You can infer the location of the drain by the behaviour of everything around it. A black hole is detected in a similar spirit. The central region does not send out light from within the event horizon, but matter outside the event horizon can become bright enough to reveal where the black hole is. The black hole is not the glowing part. It is the cause of the glow, the reason for the motion, the dark centre shaping the scene. This becomes especially clear when gas falls toward a black hole. Gas in space is not usually a neat stream falling straight inward. It has sideways motion, it has turbulence, it has magnetic fields. It may come from a nearby star, from a cloud in a galaxy, or from the crowded environment near a galactic center. Because it has motion, it tends to orbit as it falls. Instead of dropping directly into the black hole, it spreads into a flattened, rotating structure called an accretion disk. That name sounds tidy, almost like something you might find in an office filing cabinet, but the real object is anything but tidy. It is a fast-moving disk of gas where particles collide, rub, compress, and heat up. The closer the gas gets to the black hole, the faster it moves. The energy involved can become enormous. Before the gas crosses the event horizon, it can release light across many wavelengths, from radio waves to visible light to X-rays. That last part is crucial. The light comes before the crossing. Matter outside the event horizon can still communicate with the rest of the universe. It can emit light, and some of that light can escape. Once the matter passes the event horizon, its future messages are cut off, but just outside that boundary, it can be extremely bright. So when a telescope detects radiation from a black hole system, it is often detecting the final busy moments of matter that has not yet vanished from view. In a sense, the black hole is seen by the glow of material on the way in, not material already inside, not light breaking the rules, just ordinary physics operating under very extreme conditions, with gravity doing a great deal of the organizing. This is why some black holes are associated with brilliant sources of radiation. A supermassive black hole at the center of a galaxy can gather enough gas around it to produce an active galactic nucleus. When the feeding is intense, the region can become brighter than the combined light of the stars in the galaxy around it. That can sound strange at first. How can the darkest object in the universe power one of the brightest displays in the universe? The answer is that the black hole is not shining from its interior. It is acting as a gravitational engine. Matter falling into a deep gravitational well gives up energy. That energy heats the surrounding gas and escapes as radiation before the matter disappears. The event horizon remains dark. The neighborhood can be dazzling. There is also the matter of the black hole shadow. This is one of the closest things to seeing the black hole itself, though even here the wording needs care. The shadow is not a photograph of a solid surface. It is the dark region caused by the black hole capturing light that would otherwise have reached us. Around a black hole with glowing gas nearby, many light paths are possible. Some light travels from the front of the disk directly toward us. Some comes from the sides. Some light from behind the black hole is bent around by gravity and redirected toward us. But some paths lead too close and are captured. That captured light never reaches our telescopes. The result is a dark area against a glowing background. The black hole is seen not because it sends light, but because it removes light from the image. This is similar in a simple way to a silhouette. If someone stands in front of a bright window, you may not see details of their face, but you can see their outline because they block the light behind them. The person is visible by contrast. A black hole can produce a much more extreme and distorted version of that idea. It does not simply block light like a person blocking a window, because its gravity bends light around it. The shape we see is made by both the absence of escaping light and the bending of nearby light. Still, the basic lesson is clear enough. Darkness can be visible when there is brightness around it. A black hole can be recognized because it creates a hole in the light. Gravity makes this picture stranger. In normal vision, light travels in lines that we usually treat as straight. A lamp is over there, the light comes here, and the geometry is simple enough unless someone has moved the furniture in the dark. Near a black hole, light can curve strongly. A ray of light from gas behind the black hole may bend around and reach us from above, below, or the side. This means that the image of the surrounding disk can be warped. We may see parts of the far side of the disk that would normally be hidden. We may see a bright ring, not because there is a physical glowing hoop floating neatly around the black hole, but because gravity has gathered and redirected light into paths that concentrate in our view. The image is not a normal photograph of a normal surface. It is a map of light paths shaped by extreme gravity. Some light can pass very close to the black hole and nearly circle it before escaping. These paths are unstable and delicate. A slight difference can decide whether the light escapes to a distant telescope or falls through the horizon. This creates features around the shadow that scientists study carefully, because they carry information about the shape of space and time near the black hole. The ring-like appearance in black hole images is therefore not decoration. It is evidence. It is light telling us how it was forced to travel. The black hole itself says nothing from inside the horizon, but the light nearby carries a record of the curved geometry it passed through. There is another way we see black holes without seeing their own light. We watch stars move. At the centre of our galaxy, astronomers have tracked individual stars for many years as they orbit an invisible object. These stars do not drift casually. They move at high speeds along paths that reveal a massive compact centre. There is too much mass in too small a region for it to be an ordinary cluster of faint stars. The most consistent explanation is a supermassive black hole. In this case, what we see is not a glowing disk or a shadow, but the gravitational influence on stars. The stars are like markers placed around something unseen. Their motion draws the outline of the hidden mass over time. This kind of seeing is common in science. We often detect things by their effects rather than by direct appearance. You do not see magnetism itself when iron filings arrange around a magnet, but you see the pattern it creates. You do not see the wind itself when tree branches sway, but you see the branches respond. You do not see gravity itself when the moon orbits Earth, but the orbit tells you gravity is there. A black hole is detected in that tradition. It may be visually dark, but its effects can be measured. The universe supplies the surrounding objects, and those objects reveal the presence of the black hole through their behaviour. In systems where a black hole has a companion star, the evidence can be especially strong. Imagine a normal star orbiting close to a black hole. The black hole may pull gas from the outer layers of the star. That gas does not simply vanish. It forms a hot disk as it spirals inward. The disk emits high-energy light, especially X-rays, which telescopes in space can detect. The visible star may wobble in its orbit because of the unseen companion. By measuring the motion of the visible star and the radiation from the gas, astronomers can infer that the companion is both massive and compact. If it is too massive to be a neutron star and too dark to be a normal star, a black hole becomes the best explanation. The phrase "best explanation" is important. Astronomy often works by combining clues. A single observation may not be enough. A bright X-ray source alone could have several causes. A moving star alone might have several kinds of companions. But when the mass, motion, compactness, radiation, and lack of ordinary light all fit together, the case becomes strong. Scientists do not simply point to darkness and declare black hole. They build a picture from many measurements. They ask whether any normal object could explain what is seen. In many cases, the answer is no. The object must be so compact that a black hole is the natural conclusion. Sometimes what we are seeing is not light at all. When black holes collide, they can produce gravitational waves, ripples in space and time that spread outward from the merger. Instruments on Earth can detect these incredibly small distortions. This is a different kind of observation, one that does not depend on electromagnetic radiation. Two black holes can be completely dark in light and still be detected through the gravitational waves they produce as they spiral together. It is not seeing in the everyday sense, but it is very real measurement. The black holes reveal themselves through motion and gravity rather than brightness. This matters because black holes are not all equally visible. A black hole surrounded by lots of gas can be spectacular. A black hole with a companion star can be found through X-rays and orbital motion. A supermassive black hole in a galactic center can be found through the stars around it. a merging pair can be found through gravitational waves. But a black hole drifting alone through interstellar space, with little or nothing nearby, may be nearly invisible. It might only reveal itself if it passes in front of a background star and bends the star's light, causing a temporary brightening or distortion. This effect is called gravitational lensing. In that case, the black hole acts like an invisible lens. We do not see the black hole directly. We see its gravity altering the light of something behind it. This is another answer to what we are actually seeing. Sometimes we see the glow of matter falling in. Sometimes we see the shadow where light is missing. Sometimes we see stars orbiting an unseen mass. Sometimes we see jets, disks, flares, or gravitational waves. Sometimes we see background light bent by an invisible object passing in front of it. The black hole is not observed in just one way. It is known through a collection of effects, all connected by the same central fact. A lot of mass has been packed into a region with an event horizon. The jets deserve a gentle mention too, because they are among the most impressive features associated with some black holes. In certain systems, narrow streams of particles shoot away from the region around the black hole at tremendous speeds. At first, this sounds confusing. If black holes pull things in, why would anything shoot out? The key is that the jets do not come from inside the event horizon. They are launched from the surrounding environment, likely involving the spinning disk, strong magnetic fields, and the rotation of the black hole itself. Some infalling matter is redirected before crossing the horizon. The black hole system becomes not only a sink for matter, but also a powerful accelerator. Again, nothing escapes from inside. The outgoing material was never inside the forbidden region. This distinction solves many apparent contradictions. When we hear that a black hole powers a jet, we might imagine the black hole firing material out from its center. But that would violate the meaning of the event horizon. The better picture is that the region outside the horizon is active, magnetized, and energetic. Matter falling inward can transfer energy to fields and particles. Some of it crosses the horizon, some of it is thrown outward. The black hole shapes the process, but the escaping material remains outside until it leaves. The boundary is still respected. The same care applies to radiation. A glowing accretion disk does not mean the black hole is leaking ordinary light. The disk is outside. A bright ring does not mean the event horizon has a shining surface. The ring is light bent around the black hole and emitted by surrounding material. A flare near a black hole does not mean something inside has burst out. It means something outside has changed, heated, reconnected, or fallen inward in a way that produced light before crossing. The event horizon remains a one-way boundary. There is a quiet beauty in the fact that the universe lets us know so much without letting us see everything directly. A black hole hides its interior completely, yet the outside is rich with clues. The edge between knowledge and ignorance is not a failure of astronomy. It is part of the object itself. We can know the mass, we can study the spin, we can map the surrounding gas, we can watch stars orbit, we can detect waves from mergers, we can image shadows. But we cannot receive a postcard from beneath the horizon. The black hole gives us a very firm boundary between what can be observed and what can only be inferred. For the listener drifting gently through this explanation, the simplest answer is this. We're not seeing the trapped light. We're seeing the last light that escapes from outside the trap. We're seeing hot matter before it falls in. We're seeing background light bent around the black hole. We're seeing darkness outlined by glow. We're seeing nearby objects move under the influence of an invisible mass. We're seeing the universe point towards something that does not shine. This also explains why black hole images and illustrations can be misleading if taken too literally. Many artworks show a black sphere surrounded by a fiery disk, which is useful for the imagination but not always accurate in detail. Real observations are built from data at specific wavelengths, processed carefully, and interpreted through models of gravity and plasma. The colours may be chosen to show intensity rather than what the human eye would see. The ring may not look like a neat circle if the disk is tilted or moving quickly. One side may appear brighter because material moving toward us has its light boosted. The scene is shaped by motion, gravity, heat, and the limitations of the instruments. It is not a snapshot taken by a tiny spacecraft hovering nearby with a very brave photographer inside. Yet the basic idea remains steady. The black hole is visible because it changes the light around it, not because it gives back light from within. It is a dark centre revealed by bright surroundings. In some ways, that makes it more interesting than if it simply glowed. A glowing ball is easy to see. A black hole requires the entire surrounding environment to become part of the evidence. The disk, the stars, the bent light, the missing light, the jets, the waves in space, all become pieces of the same story. Now that we have separated the black hole from the light around it, we can look more closely at the brightest and most dramatic source of that light. Matter falling toward a black hole can become hotter, faster, and more energetic than almost anything else in the universe. It can turn a dark object into the engine behind a brilliant display. The next step is to follow that material as it spirals inward, not yet lost, not yet silent, but already transformed by gravity into a glowing feast around the edge of darkness. The light around a black hole begins with matter that has not yet crossed the event horizon. That is the first and most important point to keep close as we move into the glow. The black hole itself remains dark in the strict sense. It is not sending ordinary light out from its interior. But the material around it can become extremely bright, because falling toward a black hole is one of the most efficient ways nature has of turning motion and gravity into radiation. A black hole may be the silent centre of the scene, but the gas nearby can become loud with energy. If we can use the word loud for something that may be shining in X-rays, radio waves, infrared light, and other forms of radiation that no human eye could see directly. It is the surrounding matter, still outside the point of no return, that gives black holes their fiery reputation. To picture this, imagine gas drifting through space near a compact, massive object. The gas might come from a nearby star. It might be part of a cloud in the centre of a galaxy. It might be debris left behind after stars have aged, exploded, or brushed too close to something they should have avoided. In space, gas is not usually sitting still. It is moving already, even if slowly. It may have been orbiting the centre of a galaxy. It may have been pulled from the outer layers of a companion star. It may have been disturbed by a collision or a passing object. This movement matters because material with sideways motion does not simply fall straight down into the black hole. Instead, it swings around. It misses the centre. It begins to orbit. As more material arrives, the gas spreads into a rotating disk around the black hole. This disk is called an accretion disk. The name sounds calm, but the thing itself is extreme. Accretion simply means growth by collecting material. A black hole with an accretion disk is collecting gas, though not all of it necessarily falls in at once. The disk can be huge compared with the event horizon, especially around a supermassive black hole. It can be thin in shape, wide in reach, and intensely active inside. It is not a smooth, quiet vinyl record drifting in space. It is a turbulent flow of plasma, which is gas so hot that electrons have been stripped from atoms. The particles are charged. They respond to magnetic fields. They collide, swirl, compress, and drag on one another. The whole disk becomes a place where gravity, heat, magnetism, and motion are constantly negotiating. The closer the gas gets to the black hole, the faster it moves. This is not because the gas has decided to hurry, though near a black hole that would be understandable. It's because falling deeper into the gravitational field changes the gas energy. Material far from the black hole has gravitational potential energy, a stored energy related to where it is in the gravitational field. As it moves inward, that energy can be converted into motion and heat. Around ordinary objects, falling material can also heat up. Meteors entering Earth's atmosphere glow because they compress and heat the air around them. Gas falling onto a young star can shine. But black holes create a much deeper gravitational well than ordinary objects, so the energy release can be enormous. In the disk, different rings of gas orbit at different speeds. Inner material moves faster than outer material. This difference causes friction in the broad sense, though the actual physics involves turbulence and magnetic effects more than simple rubbing like hands on a cold morning. Still, the result is similar in spirit. Ordered motion becomes heat. The gas loses some of its orbital energy and angular momentum, allowing it to move gradually inward. As it moves inward, it heats up more. The inner parts of an accretion disk around a stellar mass black hole can reach temperatures so high that they shine strongly in X-rays. Around supermassive black holes, the disk may glow in visible and ultraviolet light as well, depending on its size, temperature, and feeding rate. A black hole is dark, but the gas approaching it can become an enormous lamp. This is why black holes can appear connected with some of the brightest objects in the universe. The brightness does not come from the event horizon, it comes from the disk outside it. In some galaxies, the central supermassive black hole is actively feeding on surrounding gas. The region close to the black hole can shine so intensely that it outshines the stars of the entire galaxy. These bright galactic centers are called active galactic nuclei. When they are especially luminous and distant, we often call them quasars. A quasar can be seen from across billions of light years, not because the black hole itself is glowing, but because material falling toward it is releasing energy before it crosses the horizon. The darkest kind of object can sit at the center of one of the brightest beacons in the cosmos. That is not a contradiction. It is gravity doing its work just outside the boundary where messages stop. A good everyday comparison is a water wheel or a hydroelectric dam, though again, only as a loose guide. Water falling from a height can turn machinery and produce energy, because gravity is doing work as the water descends. In a black hole system, the falling material is not turning a neat turbine built by careful engineers in waterproof boots. Instead, the disk itself converts gravitational energy into heat and radiation. The deeper the material falls before losing its energy, the more energy can be released. Black holes are very efficient at this. In some circumstances, accretion onto a black hole can convert a large fraction of falling mass energy into radiation before the material disappears. Ordinary nuclear fusion in stars is powerful, but accretion near compact objects can be astonishingly efficient. The black hole does not burn like a star. It feeds, and the meal glows on the way down. This is where the phrase glowing feast becomes useful, as long as we remember the details. The feast is not happening inside the black hole where we can watch it. It is happening around the black hole in the disk, in streams, in shocks, in hot plasma. Matter is being pulled into a faster and hotter dance as it approaches. Some of that matter radiates away energy and drifts inward. Some may be blown away by winds from the disk. Some may be channeled by magnetic fields into jets that shoot out from the region near the black hole. The black hole is not eating politely. The surrounding environment is messy, energetic, and often wasteful. Not everything that approaches gets swallowed immediately. Some material circles for a long time, some escapes, some announces the black hole to the universe in a blaze of radiation before crossing the line from which it cannot report back. The source of the gas depends on the kind of black hole system. For a stellar mass black hole in a binary system, the black hole may have a normal star as a companion. If the star is close enough, the black hole's gravity can pull material from the star's outer layers. The gas forms a stream, then a disk, heating as it spirals inward. These systems can produce strong X-rays, which is why many stellar mass black hole candidates were first found as X-ray sources. The visible star tells part of the story through its motion. The X-rays tell another part through the hot gas. Together, they point to a compact dark companion that cannot be explained as an ordinary star. Sometimes the feeding is not steady. A black hole system can flare. The disk may brighten and dim as the flow of material changes. Magnetic fields can twist and reconnect. Clumps of gas can move inward. The companion star may supply matter unevenly. To astronomers, these changes are not just flickering lights, they are clues. The timing of the flickers, the colours of the radiation, the strength of the X-rays, and the patterns of brightening and fading all help scientists infer what is happening near the black hole. Since the inner disk is close to the event horizon, changes can occur quickly around smaller black holes. Around larger black holes, the timescales are longer because the whole system is larger. A stellar mass black hole can produce rapid variations. A supermassive black hole may change over days, months, years, or much longer, though small regions within its disk can still vary in interesting ways. Around supermassive black holes, the supply of gas can come from the central region of the galaxy. Galactic centres are crowded places compared with the quiet spaces between stars. There may be clouds of gas, old stars shedding material, young stars forming, and objects moving through complicated orbits. If enough gas loses energy and angular momentum, it can drift inward and feed the central black hole. When the feeding rate is high, the galaxy may develop a bright active nucleus. When the feeding rate is low, the black hole may be quiet, as the one in our own Milky Way mostly is today. It is still massive. It still curves space and governs nearby orbits. But without a rich supply of gas falling inward, it does not shine as a quasar. A black hole can be like a campfire without wood. The possibility of heat is there, but the glow depends on fuel. The accretion disk does not always reach smoothly all the way down to the event horizon. The structure depends on the black hole's spin, the magnetic field, the amount of material, the thickness of the disk, and how efficiently the gas cools. In some systems, the disk may be relatively thin and bright. In others, it may puff up into a thicker flow. If the gas is very hot and not cooling efficiently, it may become a more swollen, turbulent structure rather than a neat, thin disk. Real accretion is not one simple picture. It is a family of behaviours. But in all versions, the central idea remains that matter outside the horizon releases energy as it falls inward. One of the most important players in this region is magnetism. Because the gas is ionized, meaning it contains charged particles, magnetic fields can thread through it. These fields can be dragged, twisted, and amplified by the rotating disk. Magnetic fields help move angular momentum outward, allowing matter to spiral inward. Without a way to lose angular momentum, gas would tend to keep orbiting instead of falling, so the disk needs a mechanism to redistribute that motion. Magnetic turbulence supplies one. The disk is not just hot gas orbiting peacefully, it is a magnetized plasma, constantly stirred. Magnetic fields are also connected to jets. Some black hole systems launch narrow, powerful jets that extend far beyond the immediate disk. These jets can travel thousands or even millions of light years in the case of supermassive black holes in active galaxies. They are made of particles moving at enormous speeds, guided by magnetic fields. It is important to say again that the jets do not come from inside the event horizon. Nothing material escapes from there. The jets are launched from outside, from the disk and the region just around the black hole. In some models, the spin of the black hole itself helps power the jets by interacting with magnetic fields anchored in the surrounding plasma. The details are complex and still studied, but the main lesson is clear. A black hole system can send energy outward, even though the black hole interior sends nothing out, because the launching happens before matter crosses the horizon. This can make a black hole look less like a simple drain and more like an engine. Matter falls inward. Energy is released. Some radiation escapes. Some material is swallowed. Some may be expelled in winds or jets. The entire system can affect its galaxy. Jets and radiation from active black holes can heat surrounding gas, push material away, and influence star formation. This process is called feedback. It means the black hole does not merely grow in isolation. It interacts with the galaxy around it. In the largest galaxies, supermassive black holes and their host galaxies appear to have evolved together in important ways. The dark center and the bright surrounding structure are part of a long cosmic relationship. The inner disk can be so hot and fast-moving that the light it emits is changed by relativity. Gas moving toward us can appear brighter because its light is boosted. Gas moving away can appear dimmer. Light climbing away from the strong gravity loses energy, shifting toward longer wavelengths. The entire image is shaped by both the motion of the gas and the curvature of space and time. This is one reason black hole images are not simple. The brightness around the ring can be uneven. One side may be stronger than the other, not necessarily because there is more gas there, but because the gas is moving in a way that beams more light toward us. When we see a bright crescent around a black hole shadow, we are seeing both hot plasma and the rules of relativity working together. There is another event that can briefly turn a black hole into a brilliant source of light. If a star passes too close to a massive black hole, tidal forces can tear it apart. The side of the star closer to the black hole feels a stronger pull than the far side. If the difference is large enough, the star is stretched and disrupted. Some of the stellar material may be thrown outward, while some falls back toward the black hole and forms a hot accretion flow. This can produce a flare called a tidal disruption event. For months, or sometimes longer, the black hole system may brighten as it consumes the remains of the star. Again, the light does not come from inside the event horizon. It comes from stellar debris heating and radiating outside the horizon, like a tragic and very luminous reminder that passing too close to a black hole is a poor long-term strategy. The light from accretion disks tells astronomers about conditions close to the black hole. Different wavelengths reveal different temperatures and regions. X-rays often come from very hot inner material or from a high-energy corona around the disk. Ultraviolet and visible light may come from somewhat cooler parts of the disk, especially around supermassive black holes. Radio emission can come from jets or surrounding plasma. Infrared light can come from dust farther out that absorbs higher energy radiation and re-radiates it at cooler wavelengths. By combining observations across the spectrum, scientists build a layered picture. No single telescope sees everything. A black hole environment is best understood by listening to many forms of light. This is one reason modern astronomy often feels less like taking a single photograph, and more like assembling a careful medical scan of the cosmos. Different instruments show different tissues of the system in a sense. X-rays reveal the hottest inner regions. Radio telescopes can map jets and image compact structures near event horizons. Infrared telescopes can peer through dust and track stars near galactic centers. Optical telescopes measure visible emission and the motion of gas. Each view is partial, but together they reveal the feeding process. The black hole is dark, but the meal is visible in many kinds of light. It is also worth correcting a common picture. Matter does not always fall into a black hole in a smooth spiral like water in a sink. The sink image is familiar, but real accretion can be clumpy, turbulent, and irregular. Gas clouds may collide. Magnetic fields may create knots and filaments. The disk may wobble or precess. Radiation pressure may push back against the inflowing material. In very bright systems, the radiation produced by accretion can become strong enough to drive winds outward. So there is a balance between gravity pulling material in and radiation or magnetic activity pushing material away. A black hole feeding at a high rate is not simply swallowing everything. It can be surrounded by outflows, winds, and jets that return energy and matter to space. This helps explain why black holes do not grow without limit at any speed they like. If a black hole is fed too rapidly, the radiation from the hot disk can push against incoming gas. There is a natural limit to how steadily luminous a feeding black hole can be before radiation pressure becomes important. In some circumstances, black holes may exceed that limit for a time, especially if the flow is arranged in special ways, but the general idea is that feeding produces feedback that can regulate further feeding. The black hole is not a bottomless appetite operating without consequences. Its own dining process can blow the tablecloth around. For all this violence, the accretion disk is also a useful clock. Material closer in orbits faster. Variations in brightness can reveal the size of emitting regions. If a flare appears first in one wavelength and later in another, the delay can suggest how energy moves through the system. If a star or hotspot orbits near the black hole, its changing signal can give clues about the gravitational field. Scientists look for patterns in the light, not because the disk is simple, but because even messy systems carry information. The glow is not random noise. It is a record of motion near one of the most extreme boundaries in nature. The disk is also where the black hole becomes visible as a shadow. Without glowing material, there may be no bright background against which the darkness can stand out. The accretion flow supplies the light. The black hole captures some of it. Gravity bends the rest. The result can be a dark central region surrounded by emission. This is why the glowing feast is not just an extra decoration around the black hole, it is part of how we know the black hole is there. The black hole creates the conditions for the disk to shine, and the disk creates the background that lets the black hole's absence of light become visible. At the edge of our understanding, the disk also reminds us that black holes are not isolated mathematical objects in the real universe. The cleanest black hole in a textbook may have only mass and spin. The real black hole in a galaxy has gas, dust, magnetic fields, companion stars, radiation, plasma, and a history. It may have grown by swallowing matter over millions or billions of years. It may have merged with other black holes. It may have spent long periods quiet and brief periods blazing. The event horizon is simple in definition, but the environment around it is rich. So when we ask what shines around a black hole, the answer is matter in its last observable stages, transformed by gravity. It is gas becoming plasma. It is orbital motion becoming heat. It is magnetic turbulence helping material drift inward. It is radiation escaping before the final crossing. It is sometimes a disk, sometimes a jet, sometimes a flare from a torn star, sometimes a whole galactic center blazing across the universe. And through all of it, the boundary remains firm. The light comes from outside. The darkness begins at the horizon. As this glowing material moves and radiates, the path of its light does not travel through ordinary space in the ordinary way. The black hole's gravity bends those paths, loops some of them around, captures others, and sends a distorted portion outward toward distant telescopes. The disk supplies the light, but gravity edits the image. To understand why black holes appear with rings, shadows, bright crescents, and strange warped shapes, we have to follow the light after it leaves the hot gas as it crosses the curved region around the dark center and carries that curved journey into the image we finally receive. The disk supplies the light, but gravity decides how that light reaches us. That is the strange arrangement near a black hole. The hot gas shines before it crosses the event horizon, but the image we finally receive is not a simple picture of a flat glowing disk. It is a picture that has been bent, stretched, boosted, dimmed, delayed, and sometimes turned almost back on itself by gravity. Near a black hole, light does not behave as our everyday eyes expect. It still travels as light should, and locally it still moves in the most direct way available to it, but the space it crosses is so strongly curved that the direct way can become a loop, a sweep, a long arc around darkness, or a path that never comes back at all. This can feel odd because we are used to thinking of a light as the straightest thing in the world. Shine a flashlight across a dark room and the beam goes from here to there. Sunlight comes through a window in a clean line, making a bright shape on the floor, and perhaps revealing dust in the air that had been minding its own business until the universe decided to illuminate it. In daily life, we treat light as a ruler. We use it to aim, to measure, to draw lines of sight. If something is directly in front of something else, it blocks it. If something is behind a corner, we cannot see it. Ordinary vision feels like straight-line geometry, but gravity changes that. In Einstein's view of gravity, massive objects curve space and time, and light follows the paths made available by that curved geometry. It is not that light has to be pulled in the same way a stone is pulled. It is not that a photon is secretly a tiny pebble with a flashlight attached. Light follows the straightest possible path through the universe, but when the universe itself is curved, the straightest possible path can look bent to someone watching from far away. Around Earth, the effect is tiny. Around the Sun, it is measurable. Around a black hole, it becomes dramatic enough to shape the entire appearance of the object. A gentle way to picture this is to imagine drawing a straight line across a sheet of paper. On flat paper, the line behaves as expected. Now imagine drawing the straightest possible line across the surface of a globe. The path may curve when you look at it on a map, even though on the globe itself it is following the natural route. Airplanes often fly along routes that look curved on a flat map because the Earth is round. The plane is not being whimsical, it is following geometry. Light near a black hole is also following geometry, but the geometry is not just the surface of a sphere. It is the deep curvature of space and time caused by extreme gravity. The bending of light by gravity is called gravitational lensing. A lens changes the path of light. A glass lens bends rays because light moves differently through glass than through air. A gravitational lens bends light because mass curves space and time. A galaxy can act as a lens, bending and magnifying the light of a more distant galaxy behind it. A star can briefly brighten the light of a background star when it passes in front of it. Even a lonely black hole with no glowing disk might reveal itself this way, if it drifts across our line of sight and bends the light of something farther away. In that case, we do not see the black hole directly. We see the background object change because the black hole has acted like an invisible lens. Near an accreting black hole, gravitational lensing becomes much more intense. The hot disk may surround the black hole in a rough plane, with gas orbiting at high speed. If space were not curved so strongly, we would see only the near side of the disk clearly, and the far side might be partly hidden behind the dark centre. But the black hole bends light from the far side around toward us. This means we can see portions of the disk that ought to be behind the black hole. Gravity lifts the hidden side into view, not physically, but optically, by curving the light paths. The result can look as if the disk has been folded upward around the black hole, as though the universe is politely showing us the back of the stage without asking whether that makes the scenery easier to understand. This is why artist impressions and simulations of black holes often show a warped disk, with material appearing above and below the dark centre. Some of that is not because the gas is actually arranged that way in ordinary space. It is because light from different parts of the disk has taken curved routes to reach the observer. The black hole acts like a gravitational funhouse mirror, though a very serious one, and not one you would want installed in your hallway. It changes what directions mean. A photon that left the far side of the disk may curve over the top of the black hole and arrive at our telescope. Another may curve underneath. Another may pass too close and never escape. The final image is a sorting of all those possible paths. One of the most important visual effects is the formation of a ring. Around a black hole, there are light paths that skim very close to the point of capture. Some photons pass near the black hole and escape after being bent strongly. Some may even swing around most of the way before heading outward. The paths that reach us from material around the black hole can become concentrated into a roughly ring-like shape. This ring is not a solid object. It is not a glowing hoop placed there by the black hole for dramatic effect, though one could forgive the universe for enjoying the look. It is a pattern made by light that has been bent around the black hole and directed toward us from the surrounding hot material. The ring also helps reveal the shadow. The shadow is the dark region associated with light paths that do not reach us because they have been captured by the black hole. If glowing gas surrounds the black hole, then there is light coming from many directions near the dark centre. Some of that light escapes to us, some does not. The missing light creates a dark area. We call it a shadow, although it is not quite the same as the shadow of a tree on the ground. A tree shadow appears because the tree blocks sunlight from reaching a surface. A black hole shadow appears because the black hole captures light that would otherwise have reached the observer. It is a shadow made not by ordinary blocking, but by the loss of escape routes in curved space and time. The shadow is larger than the event horizon would appear by itself. This is a detail that often surprises people. The event horizon is the boundary beyond which nothing can return, but the shadow includes the effect of light paths outside the horizon that still get captured. Light does not have to cross the horizon immediately to be lost. If it passes close enough on the wrong path, gravity can bend it inwards so that it eventually crosses. This makes the dark region in the image wider than the horizon itself. So when we see a black hole shadow, we are not simply looking at the event horizon like the edge of a dark ball. We are seeing the region on the sky from which light fails to reach us because the black hole has captured those paths. There is a special region outside the event horizon where light can orbit a black hole. It is often called the photon sphere for a non-rotating black hole, though real spinning black holes make the situation more complicated. Light paths there are unstable. A photon can circle, but the slightest change sends it either outward or inward. It is like balancing on the rim of a bowl so perfectly that one breath would decide whether you roll away or fall in. The existence of such near-orbiting light helps shape the boundary of the shadow and the bright ring around it. Some escaping light has travelled from the hot gas, passed close to this unstable region, and then arrived at a telescope carrying the signature of that close encounter. When a black hole spins, the picture grows richer. Most real black holes are expected to spin because the stars, gas and mergers that formed them had rotation. A spinning black hole drags the surrounding space and time around with it. This does not mean space becomes a physical liquid, but it is a useful image if handled gently. The rotation changes the paths available to light and matter. Light travelling with the spin can behave differently from light travelling against it. The inner edge of the disk can also lie closer to the black hole for certain spin directions, allowing gas to release more energy before falling in. Spin therefore affects both the light source and the lensing that shapes the final image. Motion in the disk changes the brightness too. Gas near a black hole can move at a large fraction of the speed of light. If part of the disk is moving toward us, its light can appear brighter and shifted to higher energies. If another part is moving away, it can appear dimmer and shifted to lower energies. This effect is related to the same principle that makes the pitch of a passing siren change, though light changes in colour and energy rather than sound pitch. Around a black hole, the effect can be strong enough that one side of the ring or disk appears much brighter than the other. This is one reason black hole images often look like a crescent rather than a perfectly even halo. The gas is not only glowing, it is racing. Gravity itself also changes the light. Light climbing away from a strong gravitational field loses energy. This is called gravitational redshift. Near a black hole, light emitted very close to the horizon can be stretched toward lower energies as it escapes. To a distant observer, it appears dimmer and redder than it was when it began its journey. Some light is also delayed because it takes longer curved paths. In a region where light can loop around the black hole, two photons emitted at nearly the same time from nearby places might arrive at very different times if their paths differ. A black hole image is therefore not only a distortion of space, it is also a distortion of timing. The telescope gathers light that may have taken subtly different routes through curved space and time before arriving together in the final data. The ring we see is not always a simple circle. The exact appearance depends on the viewing angle, the black hole's spin, the structure of the accretion flow, the magnetic fields, and the wavelength observed. If we look at the disk more face-on, the image may appear more circular. If we view it from an angle, the disk can look more tilted and asymmetric. Light bending can make the far side visible above the black hole. Motion can brighten one side. Turbulence can create uneven patches. The shadow remains a central feature, but the brightness around it can shift, flicker, and vary. The black hole gives the geometry. The gas supplies the weather. That is a useful word for the accretion flow in a way. Weather. Not weather with clouds and rain, of course, though after enough cosmic drama one might almost expect a forecast. The plasma around a black hole has its own storms. Magnetic fields twist and reconnect. Hot spots form and fade. Gas clumps move through the disk. Jets may launch from the inner region. The light bending stays governed by gravity. but the source of light is alive with motion. So a black hole image is partly a portrait of curved space and partly a snapshot of turbulent plasma. Scientists must separate those influences carefully. They ask which features come from the black hole itself and which come from the changing material around it. This is one reason imaging a black hole is so difficult. A black hole shadow is small on the sky, even when the black hole itself is enormous. The supermassive black holes that can be imaged are very far away. To see details at that scale, astronomers use networks of radio telescopes spread across Earth, combining them so they work like a telescope as large as the distance between the stations. This technique allows extremely fine resolution. The data are then processed to reconstruct an image. The ring and shadow are not produced by a normal camera click. They come from careful measurement, timing, calibration, and comparison with physical models. It is less like taking a vacation photo and more like asking the entire planet to become a very patient eye. When the image appears, the dark center may tempt us to think we are seeing the black hole as a black surface, but that is not quite right. The dark region is where light fails to arrive. It is a gravitationally shaped absence. The bright ring is where light from hot material has been bent and gathered into our view. The uneven brightness tells us about motion and energy in the disk. The size of the shadow tells us about the mass and geometry of the black hole. The whole image is a conversation between light and gravity, with the event horizon sitting silently at the center, allowing no message from within. This is why the phrase seeing a black hole is both true and incomplete. We are seeing the shadow cast by the black hole on the light around it. We are seeing the way its gravity bends the paths of photons. We are seeing hot gas that has not yet fallen beyond the point of no return. We are seeing the outline of something that cannot be outlined by reflected light. That may be even more remarkable than seeing an ordinary object. A black hole image is not just a picture of a thing. It is a picture of the rules of space-time operating under extreme conditions. There are also multiple layers of images near a black hole. Light from the disk can reach us by more than one path. The direct path gives one view. A path that bends around the black hole can give another, more distorted view. A path that loops even more can create thinner, fainter rings closer to the shadow. In principle, there can be a stack of these increasingly delicate images, each formed by light that has taken a more extreme route. In practice, many are too faint or too fine to resolve easily, but they are predicted by the same gravitational lensing that gives us the main ring. It is as if the black hole is surrounded by echoes of light, each echo shaped by a longer and more precarious journey around the dark center. These light echoes can carry information. If a flare occurs in the disk, some light may reach us quickly, while some may loop around and arrive later. Astronomers study such timing effects to learn about the region near the black hole. The delays and distortions can act like a map, though not a simple one. Instead of drawing roads on paper, scientists infer pathways from brightness changes and arrival times. The black hole does not let us place measuring sticks near the horizon, so light itself becomes the measuring tool. Every photon that escapes has survived a journey through curved space and brings back a small piece of the story. The bending of light also tells us why black holes can appear larger than their physical horizons. The gravity around them captures a wider set of paths than the event horizon alone would suggest. If a distant observer looks toward a glowing region around a black hole, the captured paths form a dark patch on the sky. The boundary of that patch depends on the black hole's mass and spin, and on the viewing geometry. This is why the shadow can be used as a test of general relativity. If the observed shadow size and shape match what the theory predicts for a black hole of known mass, that is powerful evidence that our understanding is working even in this extreme environment. And yet, the images are not perfect windows. The plasma around the black hole can obscure or complicate the view. The disk may be thick rather than thin. The emission may come from a broad region rather than a neat surface. The telescopes observe at particular wavelengths, and different wavelengths may reveal different structures. Dust, scattering, and instrumental limits can all affect the final image. Scientists must use models, simulations, and repeated observations to interpret what they see. That does not make the result less real. It simply means the image is a scientific reconstruction, grounded in data but understood through theory. Almost every astronomical image is like that to some degree. The universe rarely sends labeled diagrams. A calm way to hold the whole idea is this. The black hole provides 3 visual ingredients. First, it captures light, making a shadow. Second, it bends light, turning the surrounding glow into rings and arcs. Third, it changes the energy and direction of light through gravity and motion, creating bright and dim regions. The accretion disk provides the illumination. Without nearby light, the shadow would have nothing to stand against. Without the black hole, the light would not be bent into such strange shapes. Together they create the image that telescopes can detect. In ordinary life, shadows tell us that something stands between a light source and a surface. Near a black hole, the shadow tells us something deeper. It says there are directions in the sky from which light cannot arrive because space-time itself has closed the escape routes. It is a visual sign of a causal boundary. The ring around it says that light near this boundary has been curved almost beyond recognition and still escaped. The bright crescent says that the gas is moving fast, that relativity is changing its brightness, and that the disk is not a still object but a rushing flow. The whole scene is nature making an image out of absence, heat, and geometry. This is what makes black hole shadows so powerful. They turn an invisible boundary into something measurable. They let us test whether gravity behaves as expected where it is strongest. They let us estimate masses, compare models, and study plasma under conditions impossible to reproduce on Earth. They also give the human mind something it can grasp. A dark centre, a glowing ring, a visible reminder that there are places in the universe where light can approach, circle, struggle in the only way light can struggle, and either return to the cosmos or vanish from it forever. After understanding how gravity bends light into rings and shadows, the first real image of a black hole becomes much more than a blurry orange circle. It becomes a direct meeting between theory and observation, between equations worked out over a century ago and radio waves collected by telescopes spread across Earth. The image did not show light escaping from the black hole. It showed the shadow created by captured light, and the ring formed by light that escaped from hot gas around it. To see why that image mattered so much, we need to move from the idea of a black hole shadow to the moment astronomers finally gathered enough signals from across the planet to reveal one. By the time astronomers revealed the first picture of a black hole, the object itself had already been present in science for more than a century, as an idea, a prediction, a calculation, a dark possibility at the edge of what gravity could do. Scientists had seen its fingerprints everywhere. They had watched stars race around invisible masses. They had measured X-rays from hot gas falling toward compact objects. They had detected gravitational waves from black holes merging far away. They had built models, argued over details, tested predictions, and slowly gathered confidence that black holes were not just mathematical curiosities hiding inside the equations. They were real parts of the universe. Still, there is something different about an image. A measurement can convince the mind, but a picture has a way of leaning quietly into the imagination and saying, "There it is." Of course, the first black hole picture was not a normal picture. It was not taken by a spacecraft flying close to the event horizon, with a brave little camera peering out of a window and asking mission control whether anyone had packed lunch. It was not a photograph in the everyday sense, like a snapshot of the moon or a portrait of Saturn. No telescope, simply zoomed in, focused, clicked, and returned a neat image of a dark sphere in space. The first black hole image was built from radio signals gathered by observatories spread across Earth, processed through careful mathematics, checked by independent teams, compared with physical models, and slowly reconstructed into something human eyes could understand. It was a picture, yes, but it was also a triumph of patience, cooperation, timing, and the rather impressive human habit of refusing to leave impossible things alone. The black hole in that first image sits at the centre of a giant galaxy called Messier 87. This galaxy lies about 55 million light-years away. That means the light, or more precisely the radio waves used to make the image, began its journey when Earth was a very different place. No humans were building telescopes then. No one was wondering whether their internet connection would survive a video call. The signal travelled through intergalactic space for tens of millions of years before reaching our planet. And what it carried was not light from inside the black hole, because that remains impossible. It carried the glow of hot material near the black hole, shaped by gravity into a ring around a dark central shadow. The black hole in Messier 87 is enormous. It contains billions of times the mass of the Sun. More specifically, it is often described as having a mass of about 6.5 billion suns. That is a number so large it becomes difficult to feel. One sun is already enough to hold the planets in orbit, flood Earth with daylight, and make summer afternoons slightly too confident. Now imagine billions of suns worth of mass concentrated into the central region of a galaxy. The event horizon of such a black hole is vast compared with the black holes formed from dead stars. If placed in our solar system, its dark boundary would stretch across a region larger than the paths of some planets. And yet, from Earth, because it is so far away, it appears incredibly tiny in the sky. Seeing its shadow is like trying to see something the size of an orange on the moon, or a little smaller depending on the comparison you choose. It is the sort of challenge that makes ordinary telescopes clear their throats and quietly leave the room. To see something that small, astronomers needed a telescope the size of Earth. Since building a solid radio dish the size of Earth would create several practical issues, including where to put the oceans and whether anyone had enough screws, scientists used a technique that allowed many telescopes across the planet to work together. This method is called very long baseline interferometry. The phrase sounds technical, but the idea can be explained gently. If radio telescopes far apart observe the same object at the same time, their signals can be combined in a way that gives the resolving power of a much larger telescope. The farther apart the telescopes are, the finer the detail they can detect. By linking observatories from different parts of the world, astronomers effectively turned Earth itself into a single observing instrument. This network became known as the Event Horizon Telescope. The name is wonderfully direct. It tells you exactly what the scientists hope to study. Not the black hole interior, because that cannot send light out, but the region around the event horizon where light bends, matter glows, and the shadow forms. In 2017, telescopes in several locations observed the black hole in Messier 87. They had to coordinate with extraordinary precision. The weather had to cooperate at multiple sites. The instruments had to record huge amounts of data. The timing had to be accurate enough that signals gathered across the planet could later be matched together. Each telescope used extremely precise atomic clocks to mark the arrival times of the radio waves. The result was not a simple file that someone could email over after lunch. The data was so large that they were stored on hard drives and physically transported for processing. In the age of instant messages, the first black hole picture still depended on shipping hard drives around the world, which is oddly comforting. Even the most advanced astronomy sometimes has to wait for luggage. The radio waves used by the Event Horizon Telescope were chosen carefully. At the centre of a galaxy, there can be dust, gas, and other material that blocks or scatters some forms of light. Radio waves at the right wavelength can pass through much of that clutter and carry information from very near the black hole. The telescopes were not trying to see visible orange light. The famous image appears orange because the data were translated into visible colours for human viewing. The colour shows brightness, not what your eyes would see if you were safely floating nearby, which you would not be, because safely floating nearby is not one of the hobbies recommended near an active supermassive black hole. The orange ring is a visual representation of radio emission from hot plasma around the black hole. When the image was released in 2019, the world saw a bright ring with a darker centre. It was blurry, uneven, and simple at first glance. A glowing donut, some people said. A cosmic bagel. A fiery ring. Science had spent years preparing the public for a profound confrontation with the edge of space-time, and naturally the public compared it to breakfast. This was not disrespectful, really. It was human. When faced with something unimaginably distant and powerful, we reach for familiar shapes. A ring is a ring. A dark centre is a dark centre. The mind wants a handle, and if the handle happens to be a bagel, so be it. The universe has survived worse metaphors, but that modest-looking ring carried enormous meaning. The dark centre was not a surface. It was the black hole shadow, the region where light paths had been captured or bent away so that radiation from behind and around the black hole did not reach us. The bright ring was emission from hot gas near the event horizon, shaped by the black hole's gravity. One side of the ring appeared brighter because the material in the accretion flow was moving at high speeds, and light from gas moving toward us was boosted. This uneven brightness was not a flaw. It was a clue. It showed that the gas was not sitting still. It was racing around the black hole, and relativity was changing the light as it came toward Earth. The size of the shadow also mattered. General relativity predicts how large a black hole shadow should appear, given the black hole's mass and distance. The image from Messier 87 matched those expectations very well. This was a major test of Einstein's theory in one of the strongest gravitational environments ever observed. General relativity had already passed many tests, from the bending of starlight to the timing of pulsars to gravitational waves, but here was something visually direct in a new way. A shadow around a supermassive black hole, measured by an Earth-sized telescope, matching the predicted shape and scale. It was not proof in the casual sense of a single final answer, because science does not usually work by closing the book forever. It was strong evidence that our understanding of gravity still worked even near a place where space-time is curved almost beyond ordinary imagination. The image also showed what we were not seeing. That may sound backward, but it is central to black hole astronomy. The dark centre told us that light was missing. In a universe full of glowing plasma around the black hole, certain paths led to capture. The shadow was made by absence, and absence can be measured when it is surrounded by signal. This is part of what made the picture so powerful. It did not show light escaping from inside the event horizon. It showed the boundary of invisibility made visible by the glow around it. It was not a violation of the rule that black holes trap light. It was a confirmation of that rule. The picture said, "Here is where the light does not come from." To create the final image, the Event Horizon Telescope team had to be extremely cautious. They did not want to force the data into the shape they expected. Different groups worked separately, using different methods, to see what the observation supported. Only after comparing results did they confirm that the ring structure appeared consistently. This matters because a reconstructed image depends on choices. When data come from separated telescopes, there are gaps. The Earth-sized telescope is not a filled dish. It samples pieces of information, and scientists use algorithms to reconstruct the most likely image. If careless, one could accidentally create patterns from assumptions. So the teams tested, separated, compared, and challenged the result. The ring survived. The shadow remained. That process is not as romantic as imagining one perfect telescope calmly staring into the abyss, but it is more honest and more impressive. Science often advances through careful doubt. The researchers did not simply ask, "Can we make a picture that looks like a black hole?" They asked what images are consistent with the data. They asked whether different algorithms produce similar structures. They asked whether simulated observations of known models could be recovered correctly. They asked whether the result remained stable under different choices. The black hole picture was not only an image of the universe. It was an image of scientific discipline, of people making sure that wonder did not outrun evidence. The galaxy Messier 87 was chosen partly because its central black hole is so massive and therefore has a large shadow. It is far away, but its black hole is enormous. There is also a famous jet emerging from the central region of the galaxy, extending across vast distances. That jet had been studied long before the black hole image. It told astronomers that the galactic center was active and powerful. The black hole and its accretion flow are believed to be connected to the launching of that jet. Again, the jet does not come from inside the event horizon. It comes from the region around the black hole, where spinning plasma and magnetic fields can redirect energy outward. The image of the shadow was therefore part of a larger story. Messier 87 was not just hiding a dark object. It was hosting an engine capable of influencing its galaxy on enormous scales. The first image also helped people understand the difference between seeing a black hole and seeing around a black hole. The ring is not the event horizon itself. The dark shadow is not a solid disk pasted onto the sky. The colours are not natural visible colours. The shape is affected by plasma, motion, gravity, and the way the observation was made. Yet none of that makes the image less real. It is real in the way many astronomical images are real. It is data translated into a form humans can see, guided by instruments and physical understanding. When we look at pictures from space telescopes, we often see colours assigned to wavelengths our eyes cannot detect. We accept that because the colours reveal structure and information. The black hole image is similar. It is not what a human eye would casually see from a spaceship window. It is what radio waves, Earth-sized interferometry, and careful reconstruction reveal about the region near the event horizon. There is a gentle lesson here about images in science. A picture is never just a picture. It is a meeting between the universe and an instrument. A camera on a phone sees the world one way. An X-ray telescope sees another. A radio array sees another. Human eyes see only a small slice of what light can be. The first black hole image expanded our visual imagination by showing something invisible to ordinary sight. It took radio waves from hot plasma near a distant event horizon and transformed them into a ring we could look at while sitting at kitchen tables, office desks, classrooms, and probably a few sofas where people had not intended to become emotional about astrophysics before dinner. And many people did become emotional, not because the image was sharp in the way a planet image can be sharp, not because it showed spectacular detail, but because it was a direct visual connection to something once thought impossible to observe. For decades, black holes had lived in diagrams, equations, simulations, and artists' impressions. Suddenly there was a real shadow. Blurry, yes, but the universe is allowed to be blurry from 55 million light-years away. The softness of the image almost made it more striking. It looked humble. Not a polished science fiction portal, not a dramatic cinematic vortex, but a small, uneven ring of light around darkness, carrying the weight of a century of theory. After Messier 87, the Event Horizon Telescope also produced an image of the black hole at the centre of our own Milky Way, Sagittarius, a star. That object is much closer, but it is also much smaller in mass. Because it is smaller, the gas around it changes more quickly, making it harder to image. It is like trying to photograph a restless candle flame rather than a large, slow lantern. The image also showed a ring-like structure and shadow, giving another test of the same basic ideas. But the first public black hole picture remained the one from Messier 87, the first time humanity saw the shadow of a black hole directly in this way. What did that first picture show us then? It showed that the central object in Messier 87 behaves like a black hole predicted by general relativity. It showed a dark shadow of the expected size. It showed bright emission from hot plasma near the event horizon. It showed a symmetry caused by rapid motion and relativistic effects. It showed that Earth-sized radio interferometry could resolve structures on the scale of an event horizon in another galaxy. It showed that the horizon itself does not need to emit light for its presence to be revealed. It showed that darkness, when framed by glow and interpreted through gravity, can become an observable feature. It also showed us how much remains difficult. The image did not reveal the detailed interior of the black hole. It didn't tell us exactly how all jets are launched. It did not solve every question about accretion, magnetic fields, spin, or plasma behavior. It was a beginning, not an ending. Better observations, more telescopes, more wavelengths, and future space-based instruments may sharpen the view. Scientists hope to make movies of black hole environments, track changes in the rings, study flares, compare shadows, and test gravity with greater precision. The first image was a doorway. Once opened, it made the next questions clearer. There is also a philosophical comfort in it, though we will keep our feet on the ground. The black hole remained invisible at its core. The event horizon still allowed no ordinary light out. Yet humanity found a way to see the outline of that invisibility. We did not defeat the event horizon. We did not break the rules. We learned how to read the light that escaped before the rules became final. We built instruments wide as Earth, synchronized them with clocks, carried data across continents, and used careful reasoning to turn faint radio signals into an image. The black hole did not come to us. We learned how to notice its shadow. That shadow is now part of human culture. It appears in textbooks, documentaries, classrooms, news articles, and quiet conversations about the universe. It is a reminder that the most extreme objects in nature can still be studied if they leave effects outside their hidden regions. The black hole traps light from within its horizon, but the surrounding plasma glows. Gravity bends that glow into a ring. The shadow forms where light cannot escape. Telescopes collect the signal. Scientists assemble the image, and people everywhere look at the result and feel the small, strange thrill of recognizing something real in the dark. The first black hole picture did not show a monster in space. It showed a physical boundary made visible by surrounding light. It showed that black holes are not just endings, but engines of observation, because the very act of trapping light creates a measurable absence. It showed that our theories were not only written well enough to describe falling apples and orbiting planets, but strong enough to predict the shape of darkness around a supermassive object in another galaxy. That is a remarkable bridge, from the familiar pull of gravity on Earth to the ring around a black hole tens of millions of light years away. And still, images are only one way of knowing. Many black holes will never give us such a neat ring to look at. Some are quiet. Some are hidden. Some are too small or too distant for their shadows to be resolved. Some announce themselves through stars, X-rays, radio jets, gravitational waves, or the bending of background light. The first picture was historic, but it was not the only language black holes use. To understand them fully, astronomers have to listen in many ways, not just with ordinary light, and not even only with light at all. The dark centers of the universe reveal themselves through motion, heat, distortion, timing, and ripples in space-time, each clue adding another layer to the same quiet question of how we can know an object that refuses to shine. Not every black hole gives us a bright ring to look at. Some do not sit inside a glowing disk. Some are not feeding actively. Some are too small, too distant, too quiet, or too hidden for their shadows to be resolved by any telescope we currently have. If we depended only on pictures, our census of black holes would be very poor indeed. It would be like trying to learn about every animal in a forest by photographing only the ones that kindly stand in a sunny clearing. Many of the most interesting things in the universe are less cooperative than that. Black holes, in particular, are famous for not cooperating with light from within the event horizon, so astronomers have learned to notice them in other ways. They look for motion that needs an unseen mass. They look for gravity disturbing nearby objects. They look for stars behaving as if they are dancing around something dark. They listen for ripples in space-time from collisions that release no ordinary light at all. Seeing, in this wider sense, becomes less about receiving a simple beam from an object, and more about recognizing the pattern of its influence. This is not unusual in science. We often know things by their effects before we ever see them directly. No one sees the wind itself as a coloured ribbon moving through the street, but we see leaves shaking, clouds drifting, flags snapping, and umbrellas making brave but unsuccessful attempts to leave their owners. No one sees gravity as a substance pouring from Earth, but we see apples fall, moons orbit, tides rise, and people drop toast butter side down with suspicious consistency. In the same way, a quiet black hole can be known by what it does to its surroundings. It can be dark and still be detectable. It can refuse to send us light from inside and still leave clear evidence outside. The trick is to ask the universe not what shines there, but what is moving as if something heavy is hidden there. One of the cleanest examples comes from the centre of our own galaxy. The Milky Way looks peaceful from a dark field on Earth, a soft band of light across the sky, but its centre is a crowded and complicated region full of stars, gas, dust, magnetic fields, and a supermassive black hole known as Sagittarius A star. We cannot see the event horizon with ordinary eyes, and the galactic centre is partly hidden behind dust when viewed in visible light. But astronomers can observe stars near the centre using infrared light, which passes through dust more easily. Over years and decades, they have tracked individual stars moving around an unseen central object. These stars do not wander randomly. They follow tight, fast orbits, curving around a point where no ordinary bright object is visible. The most famous of these stars swing close to the galactic centre and then rush away again, like comets around the Sun but on a much more extreme scale. By measuring their positions over time, astronomers can calculate how much mass must be packed into the region they orbit. The answer is millions of times the mass of the Sun, confined inside a space small enough that ordinary clusters of stars or dark gas cannot explain it. The stars are telling us, without speaking, that a compact, massive object is there. The best explanation is a supermassive black hole. In this case, we are not seeing the black hole by its own light. We are seeing the path of stars shaped by its gravity. The orbit becomes the evidence. The dancers reveal the invisible partner. This way of finding black holes is beautifully direct in its own quiet manner. Gravity is honest. If a star moves in a certain path, something must be providing the pull. There may be details to measure carefully, but the overall logic is sturdy. A hidden mass leaves a signature in motion. Around the Milky Way's centre, the stars move too quickly and too tightly for a normal object to be responsible. If the mass was spread out across a cluster, the orbits would not look the same. If it were a collection of faint stars, the cluster would likely be unstable or visible in other ways. A black hole fits the observations in a way that alternatives do not. So the black hole is known by choreography. It is seen through the changing positions of stars across the years. The same method can work on other scales. In binary systems, a black hole may orbit with a normal star. Sometimes the black hole is actively pulling gas from the star, making X-rays in a bright disk, which is a form of light, though not visible to human eyes. But even when the gas is faint, the companion star can still reveal the dark object through its motion. If a visible star wobbles or shifts in a regular orbit, astronomers can infer the presence of an unseen companion. By studying the speed of the star, the length of the orbit, and the nature of the visible star itself, they can estimate the mass of the hidden object. If the companion is too massive to be a white dwarf or neutron star, and yet gives off no ordinary starlight, a black hole becomes the likely answer. This kind of work requires care because not every unseen companion is a black hole. Some are dim stars, some are white dwarfs, some are neutron stars. Space has many ways to hide things, which is both interesting and mildly rude. Astronomers therefore do not declare black hole every time a star wobbles. They combine evidence. How massive is the unseen object? How compact must it be? Is there any light from an ordinary star at that location? Are there X-rays or other signals? Does the motion fit a single dark companion? A strong case builds when the hidden object is heavy enough, small enough, and dark enough that ordinary explanations fail. The black hole is not guessed. It is cornered by evidence. Another method uses the bending of light from objects behind a black hole. This may sound like seeing light, and in one sense it is, because the signal we observe comes from a background star. But the black hole itself is not shining. It acts as a gravitational lens. If a black hole passes in front of a distant star from our point of view, its gravity can bend and magnify the star's light. The background star may brighten temporarily, not because it changed, but because the black hole's gravity focused more of its light toward us. This effect is called microlensing when the images are too small to separate, and we observe mainly a change in brightness. A lonely black hole drifting through space could reveal itself this way, even if it has no disk, no companion, and no glow. Microlensing is subtle, because the black hole does not leave a visible silhouette in the usual sense. Instead, the background star brightens and fades in a characteristic pattern as the lensing object passes across the line of sight. The duration of the event and the details of the brightness change can give clues about the mass of the lens. If additional measurements show a tiny shift in the apparent position of the background star, astronomers can learn even more. The lens might be a dim star, a planet, a neutron star, or a black hole. Again, the detective work depends on ruling out ordinary light sources and measuring the gravitational effect. The black hole is not seen as a lamp, it is seen as an invisible magnifying glass moving through the dark. There is something especially pleasing about that idea. A black hole which traps light that crosses its horizon can still bend the light of things behind it and announce itself by making a star briefly brighter. It is not releasing light. It is rearranging light that was already travelling through space. It borrows the background, so to speak. The star behind it becomes the screen on which gravity writes its signature. If there is no background star in the right place, we might miss the black hole completely. But when the alignment occurs, the hidden object becomes measurable for a little while, like a person briefly revealed by the shadow they cast while crossing a lit doorway. The most dramatic way to detect black holes without ordinary light is through gravitational waves. These are ripples in space-time produced when massive objects accelerate in certain ways, especially when compact objects like black holes or neutron stars spiral together and merge. Gravitational waves are not electromagnetic radiation. They are not radio waves, X-rays, visible light, or any other kind of light. They are changes in the stretching and squeezing of space itself, travelling outward across the universe. When two black holes orbit each other closely, they lose energy through these waves. Their orbit shrinks, they spiral faster. In the final moments, they merge into one larger black hole, sending a brief but powerful burst of gravitational waves across space. By the time those waves reach Earth, they are incredibly faint. The stretching they produce is far smaller than anything our senses could notice. Detecting them requires instruments of extraordinary sensitivity, using long tunnels, laser beams, suspended mirrors, and careful isolation from vibrations. The passing wave changes the length of the instrument's arms by a tiny amount, and that change can be measured. It is one of the most delicate achievements in modern science. The universe whispers by changing the distance between mirrors, and we somehow built a machine patient enough to hear it. If that does not make you fond of human curiosity, at least a little, then perhaps you have not had enough tea. The first direct detection of gravitational waves came from a merger of two black holes. No telescope saw a bright flash from that event. The black holes were dark and the merger was detected through the ripple it made in space-time. The signal told scientists the masses of the black holes, roughly how they spiraled together, and how much energy was released into gravitational waves. It also confirmed that black hole pairs exist and merge, something that had been predicted but not directly heard in this way before. This opened a new kind of astronomy. For most of history, humans studied the universe with light. Then, suddenly, we could study some of its darkest events by listening to gravity. Calling it listening is a metaphor, of course, but it is a useful one. The signals can be converted into sound frequencies, and the final sweep of a merger is often described as a chirp because the frequency rises as the black holes spiral faster. That chirp is not sound travelling through space. Space is far too empty for that. It is a gravitational wave signal translated into something our ears can understand. Still, the feeling is apt. A pair of black holes can be invisible in light and yet produce a note in space-time. The darkness does not prevent detection because the event does not depend on light escaping from the horizon. It depends on the motion of the horizons and the curved space-time around them before and during the merger. Gravitational waves also give access to black holes that may never be visible otherwise. Two black holes orbiting in an empty region with no gas around them might be completely dark electromagnetically. They could circle each other for ages without giving telescopes anything to see. But as they approach merger, their gravitational wave signal grows strong enough, if they are close enough or massive enough to be detected. In that moment, the black holes reveal themselves through the dynamics of gravity alone. This is a different kind of seeing, one that does not require illumination. It is more like feeling the floor tremble and knowing a heavy train has passed, even if the room is dark and the curtains are closed. These detections have taught us that black holes come in varieties that were difficult to study before. Some of the merging black holes detected through gravitational waves have masses larger than many stellar black holes known from X-ray binaries. This raised questions about how they formed. Did they come from massive stars in environments with few heavy elements? Did smaller black holes merge repeatedly in dense clusters? Did some form through other channels early in cosmic history? Each gravitational wave signal adds another data point. The black holes are not bright, but their mergers carry information about populations, formation histories, and cosmic evolution. There are also systems where black holes can be inferred from the absence of expected light. Suppose matter falls toward a compact object. If the object has a solid surface, the material should eventually strike that surface and release energy. A neutron star, for example, has a surface. A black hole does not have a surface outside its event horizon. Material can cross and disappear without producing a final surface impact visible to us. Comparing systems that appear similar but contain different compact objects can help astronomers distinguish black holes from neutron stars. This is a subtle kind of evidence. It is not simply seeing something, it is noticing that a certain kind of expected glow is missing. Once again, darkness becomes informative when placed in context. The absence of a surface is one of the defining observational clues. If a compact object is pulling in gas and yet lacks the type of emission expected from material, striking a hard surface, that supports the black hole interpretation. The event horizon is not seen directly, but its consequences appear in the energy budget. Matter can carry energy through the horizon rather than releasing it all outside. This does not mean every faint object is a black hole. Nature is too varied for such a shortcut. But when combined with mass measurements and other data, the missing surface can matter. Science often learns from what is not there as much as from what is. Another quiet way black holes are studied is through the motion of gas in galaxies. At galactic centers, gas can orbit around central masses, and the speed of that gas can reveal how much mass lies within its orbit. If gas close to the center moves very quickly around a small region, the inferred central mass can point to a supermassive black hole. Similarly, the motions of stars in a galaxy's central bulge can suggest the presence and mass of a central black hole. These are not as visually dramatic as an orange ring or a gravitational wave chirp, but they are important. Over time, astronomers found that many large galaxies contain central supermassive black holes, and that the mass of the black hole relates in broad ways to properties of the host galaxy. The dark object at the center is part of the galaxy's life story. There is also a method involving pulsars, should one ever be found in a very tight orbit around a black hole. Pulsars are rotating neutron stars that send out beams of radiation like cosmic lighthouses. Their pulses can be timed with extraordinary precision. If a pulsar orbits a black hole, the timing of its pulses would be affected by the black hole's gravity. This could allow very strong tests of gravity near the black hole. Astronomers have found pulsars near the centre of our galaxy, though not yet the perfect close orbit around the central black hole that would make every relativist suddenly need a larger notebook. The idea shows again how black holes can be studied indirectly. A precise clock moving through curved space-time can reveal the shape of the gravitational field. All these methods require a shift in imagination. We're used to the idea that seeing means receiving light from a thing. But astronomy has expanded that meaning. Seeing can mean watching a star trace an orbit. It can mean measuring a temporary brightening caused by lensing. It can mean detecting space-time ripples from a merger. It can mean comparing expected and missing radiation. It can mean listening to the timing of a pulsar or mapping gas motions near a galactic centre. The black hole itself may be dark, but the universe around it is full of instruments, if we learn how to use them. Stars become test particles. Gas becomes a tracer. Background light becomes a measuring beam. Space-time becomes a messenger. This broader view also helps explain why black holes are no longer speculative objects. Their existence is supported by many independent lines of evidence. If we had only accretion disks, one might wonder whether something else could explain them. If we had only stellar orbits, one might ask about clusters of dark objects. If we had only gravitational waves, one might debate details of compact mergers. But together, the evidence converges. The same kind of object explains the dark mass at galactic centres, the X-ray binaries with heavy unseen companions, the shadows surrounded by rings, the lensing events from compact dark masses, and the gravitational wave signals from merging horizons. Different tools, different signals, same conclusion. Black holes are real enough to disturb nearly every method we have for measuring the universe. There is a pleasant humility in that. Black holes do not make themselves easy. They hide their interiors completely and often hide their whole presence, unless something nearby is available to betray them. Yet human beings, on one small planet, have learned to find them through careful attention. We do not need the black hole to shine in order to know it is there. We can watch the world around it bend, orbit, flare, dim, ripple, and shift. The darkness is not a dead end. It is an instruction to look differently. And perhaps this is the deeper answer to the question that began our journey. If black holes trap light, why can we still see them? Because seeing is not limited to light escaping from a surface. Because the event horizon traps messages only from within, while the outside universe remains free to respond. Because gravity leaves patterns. Because matter glows before it crosses. Because stars move. Because light from behind can be bent. Because space-time itself can carry waves. A black hole may be dark, but it is not disconnected from the cosmos. Its presence is written into everything it influences. By now, the black hole has changed from a simple idea into something richer. It is a dark boundary, yes, but also a gravitational sculptor, a hidden mass, a cosmic engine, a lens, a source of space-time ripples, and a test of our deepest theories. The more ways we find to observe it, the more carefully we must speak about what is visible and what is not. The light we see is not from inside. The waves we detect are not ordinary brightness. The motions we measure are not guesses. The shadow is not a surface. Each clue is partial, but together they make the darkness visible in the only way it can be, through the behaviour of the universe just outside the silence. By the time we reach this point, the original question no longer feels like a contradiction. If black holes trap light, why can we still see them? At first, it sounds as though the universe has made a mistake, like placing a locked box on a table and then asking us to admire the contents. But the answer has been waiting in the distinction between the black hole itself and the region around it. The event horizon does not allow light from inside to return. That remains true. Nothing in our observations asks us to break that rule. What we see is everything that happens before the crossing, around the crossing, and because of the crossing. We see gas that heats up before it disappears. We see stars moving around an unseen mass. We see light bent by gravity. We see a dark shadow against a bright background. We see jets launched from the surrounding plasma, not from inside the horizon. We see ripples in space-time when black holes merge. The darkness is real, but it is not isolated. It is surrounded by a universe that reacts. This is what makes black holes such unusual objects. Most things we study in astronomy announce themselves by shining, reflecting, blocking, or absorbing light in ways that are fairly direct. A star shines because nuclear reactions in its core produce energy. A planet is seen because it reflects starlight or blocks a little starlight when it passes in front of its star. A cloud of gas may glow when it is heated or lit by nearby stars. A galaxy is visible because it contains billions of stars. A black hole, considered strictly at the event horizon, gives us no such ordinary surface. It does not glow like a star. It does not reflect like a planet. It does not offer a crust, cloud top, ocean, mountain range, or polite little sign reading, "Please observe here." Instead, it is known by consequence. It is an object whose presence is read through the behaviour of other things. That may seem less satisfying than seeing the thing directly, but in a way it is more powerful. Science has always been good at learning from effects. We learned about atoms long before anyone could make images of individual atoms. We learned about invisible gases by watching flames, pressure, and chemical reactions. We learned about gravity by watching falling objects and orbiting worlds. We learned about the inside of Earth by studying waves from earthquakes. Much of knowledge begins with something unseen and a trail of consequences. A black hole is one of the grandest examples. It says nothing from within its horizon, and yet the surrounding universe keeps giving testimony. The key is that the event horizon is not the outer edge of influence. It is the outer edge of return. Outside it, the universe still has options. Matter can orbit. Light can escape if it follows the right path. Gas can heat and radiate. Magnetic fields can twist. Stars can swing around and come back. A telescope far away can receive signals from the outer region. The black hole shapes those signals, but it does not have to emit them from inside. That boundary is severe, but it is not a magical sphere that shuts down physics everywhere nearby. Outside the horizon, physics is very much alive, often more alive than is comfortable to imagine. The space around a feeding black hole can be one of the most energetic environments in the universe. This is why the phrase "seeing a black hole" has to be held carefully. We see the shadow of a black hole, not its hidden interior. We see the ring of hot plasma shaped by gravity, not a glowing surface. We see stars orbiting a dark mass, not the mass shining by itself. We see gravitational lensing, where background light is bent around the black hole, not light produced by the horizon. We detect gravitational waves from black holes in motion, not beams of light escaping the dark centre. Each method reveals a different side of the same object. None gives us a postcard from beneath the event horizon. But together they give us a coherent picture, steady enough that black holes have moved from strange prediction to observed reality. There is a useful honesty in saying what we cannot see. We cannot see an event after it has passed inside the horizon. We cannot watch matter travel all the way to whatever lies at the centre. We cannot receive ordinary signals from the interior. We cannot point a telescope at the inside of a black hole and wait for an update. The horizon makes a hard observational limit. It is not a limit caused by poor engineering or insufficient patience. It is built into the structure of space-time as we understand it. Better telescopes can sharpen the ring, track the gas, measure the shadow, and test gravity more precisely, but they cannot make light escape from a region where no escape path exists. Some doors in nature are not closed because we lack the right key. They are closed because there is no outward doorway on the other side. And yet, the limit is not silence. That is the subtle part. The event horizon hides the interior, but the exterior remains deeply informative. The size of the shadow tells us about the black hole's mass and the way gravity bends light. The shape and brightness of the surrounding ring tell us about the motion of plasma and the effects of relativity. The orbits of stars tell us how much mass is packed into the centre of a galaxy. X-ray flares tell us about hot gas in the inner accretion flow. Jets tell us that magnetic fields and rotation can channel enormous energy outward. Gravitational waves tell us about pairs of black holes spiralling together and merging. The horizon hides one region, but the boundary itself creates a world of measurable effects around it. This is why black holes are not simply cosmic endings. They are also cosmic laboratories. They let us test gravity where it is strongest. They let us study matter heated to extreme temperatures. They let us watch plasma move near the speed of light. They connect the lives of massive stars to the growth of galaxies. They show us how invisible mass can shape visible structure. They have helped open gravitational wave astronomy, a way of observing the universe that does not rely on light at all. A black hole may be dark, but the science around it is bright with information. It is also important to remember that black holes are not all violent all the time. The dramatic images usually show black holes that are feeding or surrounded by glowing material. Those are easier to detect and more visually interesting. But many black holes may be quiet. A stellar mass black hole drifting alone through space could be nearly invisible unless it passes in front of a background star or captures a little gas. A supermassive black hole at the centre of a galaxy may spend long periods with very little fuel. It still has an event horizon. It still has gravity. It still is a black hole. But without a glowing environment, it may not look like much at all. The darkness of a black hole is not always surrounded by fireworks. Sometimes it is just darkness, carrying mass through space with no need to perform. That contrast is worth keeping in mind because it prevents black holes from becoming caricatures. They are not monsters roaming the cosmos, greedily swallowing galaxies whole. Their gravity at a distance is like the gravity of any object with the same mass. A star can orbit a black hole safely if it is far enough away and follows a stable path. Gas can circle for a long time before falling inward. A galaxy can host a central black hole without being devoured by it. Black holes are extreme near their horizons, but they are not supernatural predators. They are part of gravity's normal rulebook, carried to an extraordinary conclusion. At the same time, they remind us that normal rules can lead to astonishing places. A massive star runs out of support, its core collapses, and if enough mass remains packed tightly enough, an event horizon forms. No exotic imagination is required at the beginning. There is matter, there is gravity, there is pressure, there is collapse. And then there is a boundary beyond which all futures point inward. That is one of the great lessons of black holes. The universe does not need to invent fantasy to become strange. It only needs to follow its own laws into extreme conditions. The darkness of a black hole is therefore not ordinary darkness. A dark room is dark because light is absent, but the absence can be fixed by opening a curtain or switching on a lamp. A black hole is dark because light inside cannot return to outside observers. Its darkness is not a lack of illumination in the usual sense. It is a lack of possible communication. That makes it one of the clearest examples of a physical boundary in nature. The event horizon divides events that can still send signals to the outside universe from events that cannot. It is darkness as a statement about cause and effect. When we make that darkness visible, we are not undoing it. We are outlining it. The bright ring around a black hole is like the margin around a missing word. The stars orbiting the galactic centre are like footsteps around a hidden well. The gravitational waves from a merger are like the distant tremor of two dark bodies becoming one. The evidence does not come from inside the forbidden region. It comes from the world that remains outside, the world still able to send news. That is enough. In science, enough does not always mean everything. It means enough to test, to compare, to predict, to refine, and to keep asking better questions. The first black hole image made this especially clear. Many people expected the image to show a black hole in the way a photograph shows a planet. Instead, it showed a ring and a shadow. At first glance, it seemed simple: a bright orange loop, a dark center. But that simplicity was the surface of a very careful achievement. The ring represented radio emission from hot plasma. The shadow represented light paths captured by the black hole. The uneven brightness represented fast-moving material and relativistic effects. The scale matched predictions from general relativity. It was not a picture of light escaping from inside the event horizon. It was a picture confirming that light does not escape from there. The darkness was the discovery. There is something deeply human about that moment. We wanted to see the unseeable, and what we found was not a violation of nature, but a way of respecting its limits. We did not force the black hole to reveal its interior. We learned how to read the boundary from outside. We built instruments across Earth, synchronized clocks, collected faint signals, and turned them into evidence. It was not a conquest of darkness. It was a careful conversation with it, a reminder that curiosity does not always mean breaking through. Sometimes it means standing at the edge and measuring the shape of what cannot cross back. This is also why black holes sit at the meeting point of many fields. They belong to astrophysics because they form from stars, grow in galaxies, and power high energy phenomena. They belong to relativity because they are extreme expressions of curved space-time. They belong to quantum physics because their horizons raise questions about information, radiation, and the deep structure of reality. They belong to observational astronomy because we detect them with telescopes, timing, spectra, lensing, and gravitational waves. They even belong in a quieter way to philosophy because they force us to ask what it means to know something that cannot be directly seen in the usual sense. Still, we should not let the mystery become foggy. The practical answer remains clear. We see black holes by seeing their surroundings and their effects. We see glowing accretion disks. We see light bent into rings. We see shadows made by captured light. We see stars orbiting dark, compact masses. We see X-rays from hot gas before it crosses the horizon. We see jets launched from outside the horizon. We see background stars brightened by gravitational lensing. We detect gravitational waves from black hole mergers. None of this requires light to escape from inside. The rule holds. The observations work because they occur outside the rule's one-way boundary, and the story is not finished. Future telescopes may sharpen black hole images. They may reveal the fine structure of photon rings. They may watch hotspots orbit near the horizon. They may compare black holes of different masses and spins. Space-based gravitational wave detectors may hear mergers of supermassive black holes across cosmic history. Better surveys may find isolated black holes drifting quietly through the Milky Way. New theories may clarify what happens to information at the horizon and what replaces the singularity in a deeper theory of gravity. Every answer we have now creates new edges. That is not a weakness. That is how the map grows. For now, the black hole remains both hidden and known. It is hidden because no light from within the event horizon returns. It is known because the universe around it cannot help but respond. Gas heats, stars orbit, light bends. Space ripples. Images form from missing light. The dark object leaves a bright trail of consequences. That is the quiet mystery of darkness made visible. Not that black holes shine from where they should not, but that their refusal to shine can itself become part of what we observe. So as you settle deeper into the calm of this thought, picture the scene without rushing. Somewhere in a distant galaxy, hot plasma circles a dark center. Some light escapes and begins its long journey outward. Some light passes too close and is lost. Gravity curves the paths of the photons that survive. Millions or billions of years later, a tiny portion of that radiation reaches instruments on a small planet. People combine the signals, test their models, and find a ring around a shadow. Somewhere else, two black holes spiral together in darkness, and no ordinary telescope sees them. but space-time trembles, and long after the merger, instruments on Earth detect the faint passing ripple. In the centre of our own galaxy, stars continue their swift orbits around an unseen mass, returning again and again like hands on a clock whose centre is hidden. All of these are ways the universe tells us about black holes, not loudly, not simply, but clearly enough for patient observers. A black hole traps light from within its horizon, but it does not erase its own influence. It is dark, but not invisible to reason. It is silent, but not absent from the song of the cosmos, if we allow that gentle phrase just once before sleep. The light we see belongs to the edge, the surroundings, the last escape routes, the matter not yet lost. The darkness we see belongs to the boundary where those routes end. And now, here you are, a little farther along your own path than when we began. Perhaps the room is quieter. Perhaps the clock has moved on without asking permission. Perhaps the idea of a black hole feels a little less like a monster and a little more like a rule of nature drawn in. Shadow. If this journey has helped your thoughts slow down or given you something calm and curious to rest with, I would be grateful if you liked the video and subscribed. It helps this small place for gentle physics reach others who might also want to drift through the universe without being startled awake by it. For tonight, it is enough to remember this. We do not see black holes because they let light escape from inside. We see them because the universe around them glows, bends, moves, and trembles. We see them because darkness, when surrounded by evidence, has a shape, and somewhere far beyond the quiet of this moment, those dark centres remain, not waiting, not hurrying, simply existing, while light from their edges travels on through space, carrying the outline of what can never shine back. Sleep well wherever you are listening from, and may the night around you feel much gentler than the gravity around a black hole.